Dear colleagues, this is my great pleasure to welcome everybody to our annual conference on artificial intelligence in ophthalmology. This is possible due to the help and collaboration with the Ministry of Education and Science of Poland. Next slide, please. Here we see the organizers, our International AI and Ophthalmology Society, as I mentioned, Ministry of Education and Science, University of Warmia and Mazury, and our foundation, Ophthalmology 21. Next slide, please. We have also strategic partners, Alpha Event, and the company Viatris. Next slide, please. I would like to say a few words about our society. The society is a non-for-profit organization to integrate both healthcare professionals and computer scientists to share important initiatives, scientific knowledge, and practical applications of AI in ophthalmology. The society should be also involved in supporting legal regulations protecting the responsible introduction of AI to healthcare. So we invite everybody to join our group. The membership is free, and I must say that I am very glad to share that the present membership is over 1,400 members. Next slide, please. Today we have a very high quality program. We start with the Kazimierz Nojszewski lecture, and this lecture will be delivered by Professor Hao Qianlin from the Zhongshan Ophthalmic Center, Sun Yat-sen University in Guangzhou in China. He will speak on smartphone-based self-screening for ophthalmic diseases. Next slide, please. And after the talk, there will be opportunity to ask questions to Professor Hao Qianlin to discuss some issues. Professor Hao Qianlin is a director, professor, primary investigator, PhD mentor of Zhongshan Ophthalmic Center, and professor and PhD mentor of School of Biomedical Engineering in Sun Yat-sen University. He's also director of Department of Genetics and Biological Informatics at the same university. He's director of Asia Office of Afro-Asian Council of Ophthalmology, the deputy chairman of Intelligent Medical Special Committee of Chinese Association for AI, the executive vice president and secretary of Guangdong Association of Young Scientists. Professor Lin was awarded as the 24th China Youth May 4th Medal, the winner of 2021 Wenzhou Science and Technology Award for Artificial Intelligence, picked as the National Youth and Middle-Aged Technological Innovation Leaders, and awarded as Zhong Nanshan Innovation Award of Young Scientists and Technologists. He owns more than 40 patents from China and other countries. Next slide, please. Then, during the sessions, during the first session, as you see, we'll have the opportunity to listen to lectures on ABC and AI in ophthalmology by Professor Kai Jin from Hangzhou, China, then Professor Siamak Yousefi on large language models in ophthalmology from the University of Tennessee Healthcare Center in Memphis, US, and finally Professor Piers Skinner from Moorfields and UCL in London will speak on foundation models in ophthalmology, and we have a discussion again and a short break. Next slide, please. During session number 2, we will be able to listen to the talks on the clinician-driven automated label noise cleaning for multimodal retinal images by Professor Chen from Shantou University and the Chinese University in Hong Kong. I will be happy to present the talk on AI and diabetic retinopathy screening. Then Dr. Jan Wasilewski will speak on the problem of a small number of labeled examples in the diagnosis of retinopathy based on OCT images. And finally, Professor Artemiev from the University of Army Missouri will speak on predicting children's myopia risk, a Monte Carlo approach to compare the performance of machine learning models. And again, we will have a discussion. Next slide, please. And the last session will discuss AI environment regarding national and regional regulations. The first talk will be delivered by Mr. Menesh from Belgium, who will speak on European Union regulations on AI. Then Professor Alvin Liu from Baltimore will speak on US regulations on AI. Then Dr. Shayla John from Sankara Netherala in India, in Chennai, will speak on the Indian regulations, and Dr. Dong Liu from Zhongshan Ophthalmic Center, Guangzhou in China, about the China AI environment, and then we will have a discussion. Next slide, please. So now it's my, then I would like to mention our future online meetings we will have in September, and invite everybody. It is Science and Tech Innovations in Ophthalmology. Please mark the date, and you can register for this conference soon. The next slide, please. And the next we'll have the conference online meeting on presbyopia in November. Next slide, please. And finally, case reports in ophthalmology. Again, the meeting we continue to organize for last several years. Next slide, please. So now it's my great pleasure to introduce again and invite Kazimierz Nojszewski lecturer, Professor Hao-Jianlin from Zhongshan Ophthalmic Center to speak on smartphone-based self-screening for ophthalmic diseases. Please listen to this lecture.
Good afternoon, dear chairs and research fellows. I'm Hao-Jianlin from Zhongshan Ophthalmic Center, Shenzhen University, China. I'm privileged to be invited to AI in Ophthalmology 2024. I will share with you the smartphone-based self-screening for ophthalmic disease. We, human beings, receive external information for living and study, of which 90% is obtained by vision. However, there are 80 million patients suffering from different eye disease, such as cataracts and glaucoma all around the world. The ocular lesions causes visual impairment or even blindness, which significantly impact the quality of life for the individuals. The eye is the only one surface organ where blood vessels and nerves can be directly observed in a living body. So the structural and physiological features of the eyes are highly related to multiple tissue and organ systems. As the saying goes, the eye are the windows of the soul. Recently, studies have indicated that visual function can impact brain function, and the examination of the retina can help predict risk factors for system disease, including cardiovascular disease, kidney disease, and diabetes. Though eye examinations are extremely essential for diagnosis and monitoring. We are facing shortage of resources and low efficiency in traditional eye health care. Take China as example. On average, more than 30,000 eye patients are served by just one ophthalmologist, while the integration of mobile devices and the Internet of Things has innovated healthcare management. IoT technology enables various medical devices, sensors, and health monitors to be connected to the Internet, facilitating real-time data collection and exchange. Mobile devices terminals allows users to access personal health data and medical record anytime and anywhere. Specifically, each individual can monitor physiological indicators such as heart rate, blood pressure, and glucose by wearing smart devices and using apps. The data is then transmitted to a cloud-based healthcare platform. Healthcare providers can remotely access this data for real-time monitoring, analysis, and provide timely advice for referral. Given the advantages and previous application of mobile health, we need to consider how it can be better used in ophthalmology. Often eye diseases are diagnosed as you see. That means the diagnosis relies on image. However, traditional examination instruments like slit lamp, OCT are not accessible to each individual's patient. So, what can we do with smartphone? As we can see, smartphone is extremely flexible and extensible. On one hand, smartphones are already equipped with built-in camera and can be used directly to capture the eye appearance. On the other hand, with the help of different external sensors, they can achieve even more powerful functions. For example, when equipped with a portable slit lamp, it can capture anterior segment like cornea, lens, anterior chamber. Equipped with a portable fundus camera, it can detect fundus lesions. Therefore, our research group in JOC has performed a series of research and practical application and smartphones. The examples are as follows. In terms of visual impairment screening, we focus on infants aged 0 to 4 years old because they are not cooperated to visual acuity check, but the core stage of vision development. Our AI model can record and analyze their gazing behavior and facial features under the guidance of video. Based on this, it identifies visual impaired children with any of 60 ophthalmic disorders, including congenital cataracts and glaucoma strabismus. By smartphones, we have achieved home-based screening for visual functions. We have also created an app for diagnosis of ocular surface tumors. These malignant tumors on the ocular surface are relatively rare conditions, often beyond the reach of the existing healthcare system. They typically suffer from a lack of public awareness, a shortage of specialized medical groups, and limited access to medical care. In response to this critical issue, we have developed an AI diagnostic model and utilized smartphone images for early detection. Individuals can access medical education, empowering them to conduct self-examination by capturing images. Ultimately, our system can provide AI-based diagnosis, or if necessary, provide with the on-site clinical appointment. This work realized efficient large-scale screening for rare disease and shortened the pace to professional treatment. We have successfully transferred the model from professional equipment to the smartphone platform, enabling public screening at home. To solve the big problems of data heterogeneity in real world, we have improved both the quality of data and the robustness of models. We developed a human-computer interaction to standardize the capturing process in the app. We have conducted a novel smartphone-based screening approach for the malignant pigmented ocular tumors, which have demonstrated remarkable efficiency by screening over 200,000 individuals within the 6 months. In terms of new patterns exploration, we effectively leverage new media for promotion. In precision, our area under the curve AUC score reached an impressive 0.911 for an end-to-end evaluation. We have used golden standard diagnosis, ensuring the highest level reliability in our results. Intelligent follow-up is another important application for smartphone-based system. This app was developed for management of congenital cataracts after surgery. At present, the patient complains to follow-up is suboptimal. We can detect and treat the complication in time. This app can predict the timing and method of follow-up based on the patient's last follow-up examination, visual acuity or pressure, as well as the overall disease progression trends. This model achieved robust performance with an accuracy over 96%. With significantly decreased complication incidence and large amount of cost saved. This research was awarded as an excellent case of digital health care supporting clinical decision making. Actually, part of the congenital eye disease can be diagnosed prenatally for the genetic basis and predisposing factors, but conventional prenatal testing are invasive, time-consuming, and expensive. To solve the problems, we collect metadata related to demographics, child, maternal-related information, environment factors. Then we use machine learning to build a risk prediction model. To make the model accessible and available, we incorporate it into smartphone app. Compared to traditional prenatal testing techniques, this method is non-invasive, real-time, free of charge, and has an accuracy of up to 0.9, providing convenient and effective service for congenital eye disease families. Besides management of ocular disease, as mentioned at the beginning, eyes provide a window to detect system abnormalities. Mobile phones combined with portable slit lamps are used to capture images of the lens. These lenses are then analyzed in the cloud output lens age and assess the risks of developing age-related eye disease, slow self-monitoring. As shown in the right image, it can accurately assess biological age and provide an accurate reflection of the risks of age-related disease. At the same time, we have also been exploring the practice in the model of smartphone-based internet hospital. We provide AI pre-screening based on our AI medical chatbot and ocular photo-based diagnosis. Patients can upload photos of their eyes following the instructions and an AI diagnosis, as well as the referral advices will be sent to the patient's smartphones. We also provide virtual live consultation for non-emergency or follow-up cases. Immediately, the doctors will give prescription by our online pharmacy. The drug will be delivered to their doorsteps. With the support of National Key Research and Development Project, we have digitalized the ocular biological features, developed a serious intelligent diagnosis and treatment technology for eye disease, and innovated a new 3-level medical model based on intelligent technology, which has increased the prevention and treatment of efficiency of eye disease by 10 times. Currently, we have served over 10 million people. In the field of health economics, we have conducted further research to demonstrate the health economy value of our digital hierarchical screening. The results show that annual digital screening with smartphone plus AI is the most cost-effective method in both urban and rural China. The advancement of mobile application and the Internet of Things leads to increased data diversity and complexity, posing heightened demands to medical data security and sharing. To address this issue, we developed a digital mask technology for normal de-identification and built a randomized clinical trial framework to improve data management for multi-center randomized clinical trial. Digital mask is based on real-time 3D reconstruction and deep learning to retain the clinical attributes contained in patient videos, while minimizing access to non-essential biometric information for added personal privacy in clinical practice. We constructed an AI and blockchain-based data management framework for RCTS. In our designs, blockchain technology ensures data integrity and AI aims at objectively and combined both to efficiency. We implemented the framework on a post-market RCT after security and optimization perform tests on the application. The AUCS of AI algorithm exists 90%, and the blockchain network prevents unauthorized falsification with a response less than seconds. Therefore, invited experts risk the consensus that this framework can be a solution for integrity, objectivity, and efficiency with a website illustration. In summary, with the help of smartphone and mobile healthcare, we have established a series of eye health management applications. In terms of medical service, we have achieved disease screening, triage, diagnosis, personal treatment, and follow-up. At the lifestyle level, we conduct real-time health monitoring, disease risk prediction, and personalized behavioral intervention from the microscope of living environment. We have launched the project of China City Eye Health Index. Hope the future discoveries can help provide guidance for city planning. Approaching the end, I'd like to briefly introduce Zhongshan Ophthalmic Center, JOC. JOC is the leading eye hospital in China. We now serve as the WHO Collaborating Center for Eye Care and Vision and host the headquarters of Asia Pacific Academy of Ophthalmology, APAO. JOC serves as a national educational base for PhD students and clinical residency in ophthalmology. Our graduate students and alumni have achieved national recognition, with many becoming professors at renowned international universities. Its commitment to exceptional patient care, education, and cutting-edge research and global collaboration, JOC remains at the forefront of ophthalmology in China. That's the end of my talk. Looking forward to your visit to Guangzhou, China, with the prospect of a close and productive collaboration with you all. Thank you.
Good afternoon.
Good.
Dear chairs, good afternoon. Dear chairs and research fellows, I'm Dong Liu and I'm from Zhongshan Ophthalmic Center, Sun Yat-sen University, China. And now I am on behalf of Professor Hao Tianling to join this discussion.
Thank you. I mean, it's a pity that he could not join personally, but of course we understand that. So let's open the discussion. Everybody is welcome to put the question on the chat. This is the chat for. Yeah, so, well, please share congratulations to Professor Lin for very interesting presentation at first. He raised a lot of different topics, and of course we are quite aware that from this picture, as he shown shortly, is a source of many informations, not only ophthalmic but also demographic, also systemic disorders information. However, and of course, smartphone picture has many advantages, but of course there are many, I would say, potential limitations. So my first question, well, regarding just taking photos from the smartphone, how to standardize the quality of the photo? Because as we know, well, with the table fundus camera, when the photo is taken in a very standard situation, I mean there is no movement of the head, or it is very much limited, and many aspects of this photo are standardized. But even with that, I mean, we do have a discussion if, for example, particular algorithm trained on one fundus camera images can perform well on another device. So even the standardization is much better. How to work with, for example, with the pictures taken from the smartphones? I mean, this is my first question.
Okay, thank you for your question. With the help of smartphone and mobile healthcare, we have established a series of eye health management applications. In terms of medical service, we have achieved disease screening and tracking diagnosis, personalized treatment, and follow-up. You mentioned that the image quality from different smartphone or devices. We have established a smart quality system to improve the different image from various devices. So we can ensure the quality of image from different smartphone. We have take photos. So we have established this system. Yeah.
Is it already published, or is it possible to test this system? I mean, finally, we really appreciate nowadays when the different teams share or make it available to use their algorithm by others. Is it available to be used by others or not? To test it, to verify it?
Yeah, it's that. We have established this system and we have published in the MPJ Digital Medicine, the niche group, the journal belong to niche group, and this system will open to others to other researcher to applicate to application in the future.
So
yeah.
So, as I understand, you are open for, let's say, other researchers' approaches to test your models. Yeah. Do I understand it well?
Yeah. We believe that in the future we will share this system with other researchers all over the world. We believe that this system can improve our smartphone-based healthcare, so it is useful to us.
But you mean in the future, not now?
It's that and currently we have improved our system, and it will improved step by step.
So, because you think that it's not ready to be not only used but also tested. So this is just you work on that, yeah. But really, you have nothing against making it available for others, as I understand, yeah.
Yeah. It's so.
Okay, we still have no questions, but well, let me ask. Professor Lin mentioned about the study. I know this study. This was published in Nature Medicine about the vision impairment screening in children. Could you share with us what is the present situation with this project? I mean, or the future? Do you plan to introduce such a device to be for practical application in China or worldwide?
Yeah, absolutely. We will perform it to the real world study. Now we have done it in China, and we will take to all of the world. We are now taking it to other countries. Yeah.
So I don't understand. So have you started any studies outside of China with this approach or not?
We will plan to use it in other countries.
Okay, this is a plan. Okay, of course, yeah.
Yeah.
And
Yeah.
in the China, because well, you have already studied it. Do you need any additional work to, let's say, register it in China? Do you think about that? About the formal registration in China?
Yes, in China, the government will encourage us to use these smartphone-based technologies to screening children's ocular disease. So we will perform it in the China of the different provinces.
Yeah, we have a question. Hello, great presentation, great solution. I wonder if any other metrics than accuracy was assessed. Do you have any analysis per disease, perhaps, in various age groups?
Mm. So we believe this technology will help us to the ocular disease screening of children, and it will uh, it will it will disease the occurrence of ocular disease.
We have another question, but I will read it, but it's not probably well addressed to you. I mean, or Professor Ho Chi Lin. Hi, thank you for all. I'm looking to develop an AI model which will be integrated or embedded on a smart glass or smart lenses. How can I have stakeholders for this objective? Is there any possible collaboration? I am Kala Dual, AI research and medical image processing field. So I will try to respond to that, because this is to some extent the role of the society. I mean, you can use the society as the member of the society. You can send the email and we will try to network. I mean, we work on such a engine, let's say search engine, something that could help to network our members to a specific projects. So people who are interested in one topic, that they could contact other people globally interested in the similar topic. So hopefully at the end of this year, we will be able to present something. Now we work on the sections. We have several sections of the society. You can check them on our website. And we have already organized a few section meetings. A few more will be conducted soon. And then in July, we'll send a newsletter to all members with the section minutes. And this is, I think, how the society can be used. Yeah. Okay. So.
Well, yeah, thank you for your comments. Yeah.
Yeah, I think that
Okay.
now we have a time.
Thank
Oh,
you.
you hear the voice of the timer says that our time is over and we need to move to the first session. Thank you so much for being with us, and please thank again Professor Ho Chi Lin for a very informative and visionary presentation regarding the use of smartphone in the future. Thank you.
Thank you.
Now we can move to the first session.
Okay. Bye-bye. Goodbye.
Bye-bye.
Hello, everyone. Hello, Chairman. Thank you for the invitation. I'm Jin Kai from Eye Hospital of Zhejiang University, and today my topic is exploration of artificial intelligence and large language models in ophthalmology. Over the past decades, the revolution of technology in ophthalmology has been remarkable. The transition from traditional machine learning technology to deep learning methods and eventually to the development of large language models. Here is the representative achievements of AI in ophthalmology in recent years. In 2016, the JAMA published a paper of deep learning screening diabetic retinopathy, and then in 2017, the Nature Biomedical Engineering published the cataract screening. In 2017, the JAMA published a paper using deep learning to screening multiple eye diseases. Then, in 2018, the cover article of Cell published using transfer learning to screening eye diseases and pulmonary diseases. In 2018, Nature Medicine published a paper of using OCT images to screening multiple eye diseases. In 2021, the Lancet Digital Health published the prediction of liver disease. Then in 2018, the Nature Biomedical Engineering using the AI to predict cardiovascular diseases. In 2021, the Nature Communication published the paper using the AI to diagnose keratitis. In 2020, the New England Journal published a paper using AI to diagnose optic pulmonary edema. And then in 2022, the paper in clinical medicine can diagnose 30 retinal diseases using deep learning. And then in 2021, the Lancet Digital Health published a paper using AI to quantify the geographic atrophy in AMD. In 2023, in Nature Communication, published a paper using AI to predict the lens biological age and the eye disease and systemic disease. Also in 2023, in JAMA Network Open, AI can prediction of depression. We've transitioned from traditional machine learning techniques to deep learning techniques, and now to the development of large language models. This progression has not only expanded the scope of application to encompass multiple ocular conditions, but also shifted objectives from simple screening tasks to complex predictive analytics. These advantages has been expanded to predicting systemic disease using ocular biomarkers. And here is the paper last year in Nature. And a foundation model was built to generalize disease detection from retinal diseases. And here's a concept of fundus imaging plus AI CAT screening and the prediction of eye and systemic diseases. And take a fundus photo, you'll know if you have eye disease or chronic disease. And let's take a look at the current status of eye healthcare in China. And first is the imbalance of medical services, imbalanced distribution of medical resources and uneven levels of medical service in different regions. And second is the scarcity of the resources. And there is a data 46,000 Chinese people who can treated by one ophthalmologist. and the limited efficiency, it takes nearly 1 minute to for an ophthalmologist to interpret an image, and AI can process 10 images in a second. So AI can lead the cost savings and improve the efficiency. However, despite the advantages, several challenges of AI in ophthalmology persists. The data quality issues are widely presented throughout the whole life cycle of medical artificial intelligence research, including model construction, performance evaluation, and clinical applications. Numerous technical and imaging factors influence the performance of deep learning systems. So the data quality is the bottleneck issue in the ophthalmology AI research. The second part is our research team using the data-driven AI to assist diagnosis in ophthalmology. At the onset of our AI research, we propose a fundus image quality evaluation system based on human vision system to evaluate the image quality of the color fundus photos. And then we propose an algorithm to enhance the low quality fundus images. And finally, we establish a computer-aided diagnosis system to diagnose IDDs like diabetic retinopathy, age-related macular degeneration, and glaucoma, and systematically improve the quality evaluation and improvement system for the fundus images and integrate a set of image pre-processing algorithms and overcome the difficulties in constructing standardized databases for IDDs. And based on the algorithms, we established a standardized multi-source heterogeneous database, and we established a fine-grained annotation of various IDDs databases, and also a longitudinal fundus dataset to promote predicting of the prognosis of IDDs, and also multi-source heterogeneous databases for AI generalization. And we published 3 papers in scientific data. And then we focus on the single IDD screening. We've conducted numerous studies on AI-assisted decision-making. And for instance, we've developed a biomodality deep learning system to grade the severity of age-related macular degeneration using OCT and OCTA, and also OCT and IR images. And we can diagnose the grade of AMD with an impressive overall accuracy of 95%. And we also can use the multimodal detection of glaucoma and also have high accuracy. And then we shifted to the multiple disease screening. And here is the paper of our team published in the eClinical Medicine. We used the ultra-wide retinal images to build a deep learning system for the diagnosing 30 kinds of common retinal abnormalities. And there's also a paper by another team to use deep learning platforms for classification of 39 types of retinal abnormalities, which is published in Nature Communication. And we also did detect these in ultrasound images and detected these in pathological images. And targeting the clinical needs, we quickly identify common diseases in clinical patterns. And then we explore the imaging biomarkers, aim to explore the mechanism which is relevant biological biomarkers play a role in the disease occurrence. We first use the imaging factors and inflammatory indicators in DME, which is published in Ophthalmology and Therapy, and we also explore the imaging features with the inflammatory indicators in wet AMD. And this is the findings of disease prevention and treatment decision making. Then we shifted to the prediction of treatment response. We know the anti-VEGF therapy is a hot topic in ophthalmology in recent years. So we collected the OCT images of the patients and using the machine learning to prospective prediction of disease progressing and the treatment response. And we also used photos of the post-operative images of the eyelid surgeries, and we can develop personalized diagnosis and treatment strategies for patients. Then the third part is the breakthroughs in large language models, which is a hot topic recently. And we know the generative AI and the large language models is the most hot topic in medicine this year. And we aim to explore the next generation of AI in ophthalmology. And here's the paper in Nature Medicine using a visual language foundation model for the pathology image analysis using medical data. And the innovative application in medicine are booming due to the progression of generative AI, and medical tasks can be done by the large language models with no need to train foundation models from private data. And then the large language models merely trained on open datasets and equal or outperform than the specialists in most clinical summary tasks, and reducing the documentation burden with the large language model in clinical workflow. And here's used the paper in Nature Medicine also used the fine-tuned large language models for clinical summary tasks such as radiological reports, patient questions, progress records, and doctor-patient conversations. And this paper in eBiomedicine last year using the czerwca to perform fast reaching the 80% accuracy on the myopia-related questions, and application for patient education and self-diagnosis may improve the utilization of the medical AI. And our team also exploring the czerwca to interpret FFA reports. And here's the figures, and we using the czerwca English perform best with the F1 score of 80% lower than the specialist 89%, but close to the ophthalmology intern 82%, which is published in this year. While the application of large language models in ophthalmology holds promising prospects improving patients' medical experience. However, challenges such as data privacy, security, and the complexity of integrating large language models into clinical workflows must be addressed. And that's all. Thank you for attention.
Hello, my name is czerwca Yousefi. I'm assistant professor with the Department of Ophthalmology, University of Tennessee Health Science Center in Memphis, and today I'm going to talk to you about some applications of humanoid robots and large language models in ophthalmology. Here are my disclosures. I want to also acknowledge our funding support and the contribution of all of my lab members. Let's just start off with humanoid robots. Humanoid robots can be easily recognized by their human-like characteristics. They are receiving more attention in healthcare overall and in ophthalmology in particular. They have a number of advantages. For instance, they can provide a more natural physician and patient interface and interaction. They can also benefit clinical operations as well as patient engagement. That I'm going to talk about a number of applications. They also accompany with a number of challenges. For instance, they can be highly dependent on AI decisions on training datasets. So training datasets can be limiting factors. There are a number of ethical implications of robotic intervention in healthcare as well. And also integration with AI, it requires a lot of investment in infrastructure and training datasets.
Hello,
Hello, I am happy to see you.
can you introduce yourself?
Sure, I am Albors. I am an intelligence robot and want to be a great digital ophthalmologist. I am working on different artificial intelligence models for recognition different data aids.
What's your job?
I am going to be a digital ophthalmologist. I am working at data mining and machine learning laboratory at University of Tennessee Health Science.
Hello,
So this was Albors, and our aim was to train Albors to, as he also mentioned, become a digital ophthalmologist. And we wanted to start with glaucoma. So for this purpose, I trained and developed an algorithm based on the ocular hypertension treatment study, in short, OATS dataset. OATS dataset includes over 1,600 subjects, close to 43,000 fundus images that about 39,000 belong to non-glaucoma eyes and close to 4,000 belong to eyes with glaucoma. So the algorithm, the CNN model, was developed based on this dataset, and then it was externally validated based on two independent publicly available datasets. These include ACRIMA dataset with about 700 fundus images, and then RIM1 dataset with about 450 fundus images. This is the overall architecture of the model that we developed. It included a number of steps. At the very first step, we wanted to make sure that we can send fundus images to Albors based on local resources or based on cloud. Then we trained and tested the Albors based on CNN models. Particularly over here, we use the domain adaptation that uses both labeled data and unlabeled data. So the other differences between domain adaptation model that we developed and a simple CNN architecture is that we used different resolutions as well as multiple loss functions to make sure that the accuracy is as high as possible, and at the same time the model is generalizable and also robust. So this is the overall architecture. And then we ultimately validated the model based on 2 data sets. Here is the ROC curve of the model that we developed based on external data sets. And these external data sets, as I mentioned, include ACRIMA, that the area under the ROC curve was 0.87, and then RIM1, which was 0.92. Remember, the original model that we developed, the area under the ROC curve was close to 0.96. So pretty much generalizable without compromising the accuracy. And then we just wanted to see whether now we can talk with Albors, send the fundus image to Albors, and then Albors can run the AI model and then get back to us with a response. So here is what we performed.
Would you like to show me your fundus photograph that I analyzed by a deep learning model and see can I see the sign of glaucoma or not?
And here is a fundus image of an eye which is normal.
Great! Your fundus photograph was analyzed by a deep learning model and I see no sign of glaucoma. It is healthy.
And then here is an example of a fundus photo from a patient with glaucoma.
Your fundus photograph was analyzed by a deep learning model and unfortunately your optic disc looks suspicious.
Okay, so Albors has a number of other applications, particularly in ophthalmology. It can be used for diabetic retinopathy detection as well, for age-related macular degeneration or AMD, for retinopathy of prematurity or ROP, and even other applications. So what we developed in Albors was in glaucoma, but again, it is possible to use it for various other retinal conditions as well. In particular, Albors can be used in pediatric ophthalmology even without those AI models that we developed. And this is as an example of how Albors can interact with kids. For example, it can be used for all kids, particularly those with some conditions. For example, kids with autism. Typically, they are inattentive, and it's highly challenging for pediatric ophthalmologists to measure their vision characteristics. Assume that Albors can interact with them. Kids typically like robots, and they are excited, and they are typically become more calm and more attentive. So that's why it is possible to make those kids with particular conditions like autism more attentive. Then it is possible to measure their visions better and then improve the outcome. This is one of the great applications of humanoid robots like Albors in pediatric ophthalmology. Okay, the reason I talked about Albors before large language models, or in short LLMs, is that Albors was also equipped with natural language processing, NLP. And our intention early 2022 that we acquired Albors was to make Albors a digital ophthalmologist that is equipped with NLP, so we can talk with Albors. Albors can understand us, we can understand Albors, and then Albors can analyze and interpret fundus images and then get back to us with major retinal conditions. But towards the end of 2022, late 2022, LLMs, particularly ChatGPT, was introduced that could pretty much whatever that we intended to do now could be done with LLMs, and that's why we just switched to large language models more than working on Albors. So this is a ChatGPT that was introduced. This timeline shows pretty much the introduction of most of the prominent LLMs over time. So ChatGPT is a generative AI, a large language model powered chatbot. It was fine-tuned based on GPT 3.5 architecture through reinforcement learning and supervised learning methodologies based on vast textual data derived from the internet. Many applications, text classification, general question answering, most of these, in particular in ophthalmology. The very first applications and studies were on evaluating performance on basic and clinical science course and optho questions. A couple other studies on evaluating performance of ChatGPT answering ophthalmology case challenges. And then later on, many publications appeared, and I'm sure that you know and you have read most of those. So in ophthalmology, a few things that I want to explain over here that were done in our lab. So we worked on 3 ophthalmic disease diagnosis from case reports in neuro-ophthalmology, in cornea, and in glaucoma. 2 of those has been published, 1 still under review. And then we also conducted 2 studies on OATS based on large data sets, close to 1,600 subjects, 3,200 eyes for both diagnosis and glaucoma prediction. One of these papers also appeared a few weeks ago. Get back to the very first 3 studies that were on glaucoma, cornea, and neuro-ophthalmology. This is based on a database, an online database that is available. And then the number of cases for each study was, for glaucoma it was 11, for cornea it was 20, and then for neuro-ophthalmology it was 22. And then we just compared 2 wings, the ChatGPT with clinical expertise or ophthalmologists. This is an example of a detailed case report on the left. We then show the fundus images to the ChatGPT. We just created a prompt, from the detailed case report, and the prompt has been shown on the right-hand side. And you know that prompt engineering is very important. That's why we just worked on how to articulate the prompt a lot, actually, and then checked based on a number of different scenarios. We evaluated in most of the studies both ChatGPT 3.5 is a public version, and then ChatGPT 4.0 is a commercial version of ChatGPT. And over here I'm showing a couple of examples of prompts that we generated from detailed case reports. Here are more examples, again on the left hand side for public version, and then on the right hand side for the commercial version of ChatGPT, the prompts that were generated. So let's go to clinical evaluations. For glaucoma subtypes, we only compared ChatGPT 3.5, which is public, with 3 senior ophthalmology residents. This was the very first study that we did, so this was the oldest study. And we observed that the ChatGPT, the public version, the accuracy was close to 73%, while 3 senior ophthalmology residents, the average accuracy was 67%. So ChatGPT, the public version, was a little bit more accurate compared to 3 senior ophthalmology residents in terms of glaucoma subtype diagnosis. In terms of corneal diseases, we compared both ChatGPT public and commercial version with 3 corneal specialists. Pretty much all 3 were very highly experienced corneal specialists. ChatGPT, the public version, the accuracy was 60%, the commercial version was 85%, and then 3 corneal specialists, the accuracy was 93%, which was better than the commercial version of ChatGPT. And then in terms of neuro-ophthalmology, compare the public version and the commercial version with two neuro-ophthalmologists, pretty much both of them young neuro-ophthalmologists, and ChatGPT accuracy was 82%, the commercial version, compared to 86 and 86% of the first and second neuro-ophthalmologists. So the agreement was pretty much good. For example, for neuro-ophthalmology, the very first one and the second one, they had great agreement with the commercial version of ChatGPT overall. So regarding the last two studies that we did based on the ocular hypertensive treatment study, in short, OATS, let me first talk about OATS a little bit, because this data set was larger, and these two studies, as I said, one of them has been published in American Journal of Ophthalmology, the other one is still under review. So OATS itself is a randomized clinical trial with 22 contribution of 22 centers in the US. It was a longitudinal study. It has a number of phases. Phase 1 and 2 that we used started in 1994 and then ended in 2009. It included patients with ocular hypertension, in short OHT. The intraocular pressure, or IOP, should be greater than 21 millimeter of mercury for the patients to be included, and then no sign of glaucoma at the time of recruitment. So these patients were at the risk of glaucoma, and then over time they developed glaucoma. About 1,600 participants in 2 wings, pretty much half-half in the observation and then medication group. The parameters that we used include these 4 categories. Demography included age, gender, and race, and then clinical ocular, we used intraocular pressure, central corneal thickness, visual acuity, and visual field, MD. For disease history, family history of glaucoma, history of blood pressure, and then other history of disease, and then optic nerve head characteristic, horizontal cup-disc ratio, disc hemorrhage, retinal hemorrhage, notching rim, and thinning of disc rim. These were the parameters that we used. So then what we did was to automate this workflow, because there are 3,200 eyes. It is not easy to manually create a case report, from the case report a prompt, and then give the prompt to ChatGPT and then record the outcome. So we had to automate all of this pipeline. The very first one, we based on these the parameters that I explained in the previous slide, we created a case report. Then from the case report we generated a prompt, and then we made sure that the prompt is optimized, and then we fed the prompt to the model and then got the outcome. The whole process was automatic. So we used the API of ChatGPT for doing so. That was LangChain. So anyways, for prompt engineering, final question was very important. These are the lessons that we learned. For example, if you use any of these 3 type of final questions in your prompt, you will get a different outcome. For example, for a subset of the OATS dataset, close to 200, we observed that the area under the ROC curve can be different. For example, for this type of prompt, it was the best. So we used this prompt in our downstream analysis. So prompt, as I said, prompt engineering is very important. These are the combination of the parameters that we also just analyzed. For example, for demographic, clinical, ocular, visual field, optic nerve head, and disease history, we got these, we obtained these outcome for public version and then for the commercial version. But anyways, what we identified was that demographic, clinical, ocular, optic nerve head, and disease history provide us the highest accuracy. It means that visual field information was not included in this. So these were based on again based on a subset of the OATS, but the final analysis, this is the outcome of the final analysis. We obtained an area under the ROC curve close to 0.76, accuracy of 87%. Pretty much this was what we obtained. But is this good enough? You know that the CNN models based on fundus images from the same study from the OATS that we published a few papers. Others also have published papers based on the OATS. We obtained area under the ROC curves over 0.90. but ChatGPT, based on some of the parameters, just the textual parameters, the accuracy in terms of area under the RC curve is 0.76. So still close to 15% difference between the area under the RC curve of a CNN model based on fundus image only and the public version of ChatGPT that we used last year. These are the studies from the last year. So still a lot of room to improve. So in conclusion, so Albors or the other type of humanoid robots can communicate the outcome of diagnosis with both physicians and patients. It's very important. Albors is being trained to ultimately function as a future digital ophthalmologist, digital glaucoma expert, and pediatric companion ophthalmologist. These are various applications that can be explored in the future. Humanoid robots like Albors may function as the next generation AI models in research, clinical practice, and educational setting. We expect Albors to improve visual testing and diagnosis, and to creation of educational programs as well that will engage children in pediatric ophthalmology as well as those who are interested in ophthalmology. So Albors can augment both general and pediatric ophthalmology, considering the low number of pediatric ophthalmologists. So that's why I'm emphasizing on the pediatric ophthalmology. Why? Because Albors, even without any embedded CNN-based AI models or transformer-based AI models, can be used in pediatric ophthalmology. But if it is equipped with AI models, CNN models, transformer-based models that are highly accurate, it can complement clinical practice as well. It can be used even for screening for educational purposes too. So ChatGPT has comparable performance with human expert in diagnosis of glaucoma, neuro-ophthalmology, and corneal diseases based on detailed case reports and 3 studies that we conducted, but these were based on close to 20 cases that we had. The overall accuracy of ChatGPT 4, the commercial version, was consistently higher than ChatGPT 3.5, which is the public version. This is also very important to know. Current ChatGPT has no multimodal capabilities. So at the time that we conducted this study, we know that now ChatGPT has been equipped with a number of multimodal capabilities, but based on the reports, still there's a lot of room to improve. For example, a ChatGPT, multimodal ChatGPT, or ChatGPT based on fundus photograph, and a CNN or transformer-based AI model based on fundus photograph. So the accuracy of ChatGPT is close to 15% lower than corresponding conventional neural network based on images. I discussed this, and incorporating multimodal data with image processing capabilities can increase the likelihood of integration of ChatGPT in ophthalmology. So with that, I'm going to conclude the talk. Thank you so much, all of you, for attention, and thank you so much, and thank the organizers for inviting me to talk about some of the applications of ChatGPT in ophthalmology based on a number of research, a number of studies that we conducted over the past few months and last year. Here are my information. You can reach me out through this email, and here is the lab website and the university.
Good afternoon. My name is Piers Keane, and today I'm going to be talking to you about foundation models in ophthalmology. If anyone would like to get in touch, I've got my Twitter handle in the bottom right corner of this slide, and on the last slide of my presentation, I'll also give my email address. For those of you who don't know me, I'm a consultant ophthalmologist in Moorfields Eye Hospital in London. I'm a professor of artificial medical intelligence at University College London's Institute of Ophthalmology. I'm funded by UK Research and Innovation, and these are my financial disclosures. So the exciting thing in artificial intelligence is that, believe it or not, our progress has been accelerating over the last 2 years. And so The Economist talked about this in a cover story in July 2022, where they talked about AI's new frontier. And in particular, they talked about how huge foundation models are turbocharging progress in artificial intelligence. And if you can read the subheading there, they say that that these models can have abilities that their creators did not foresee. So what are foundation models? Well, foundation model is a concept that was first described in 2021 by this large group led by some professors at Stanford, and essentially describes very large, very complex models that are typically trained on huge amounts of unlabeled data and which can then be fine-tuned with small amounts of labeled data for a diverse range of what are called downstream tasks. So essentially you get one very big model, and that very large model can be then used in lots and lots of different applications with only a small amount of fine-tuning. Now, if you're interested, just in the last week or two, we've published a review article in the British Journal of Ophthalmology on foundation models in ophthalmology, which goes into the history of this and goes into the field in a lot more depth. Now, there are a couple of key features of these foundation models that I think are worth highlighting. The first is that they have a different approach to machine learning, a different learning approach. And that's something called self-supervised learning. And so that's different from the traditional approach, which is called supervised learning, where you have to explicitly label each bit of data that's used. And so one of the big advantages of these foundation models is that they can typically be trained on huge amounts of unlabeled data. And so, for example, imagine you have a situation where you have 1 million color fundus photographs, but you don't have any diagnosis or any labels for those photographs. You could use those to create a foundation model, but you would have struggled with the previous types of supervised learning, because how would you get, ophthalmologists and retina specialists to be able to label 1 million scans? The other big difference with these foundation models is that they use a different type of neural network architecture. And they use something called a transformer architecture. And the transformer architecture was first described by a team from Google in a preprint in 2017, and they called it "Attention is all you need." So I think they were sort of making a joke about the Beatles song "All You Need Is Love." And essentially, this paper has been one of the most influential papers, not just in computer science, but more broadly. It's been cited nearly 200,000 times in the 7 years since it's been published. And credit where credit's due to Google, because they didn't try to patent this. They made this available as an open source code. If you're interested in learning a little bit more about the history of that particular paper, Attention is All You Need, it's a very nice article in Wired magazine in March 2024, which talks about how these 8 Google employees invented modern AI and gives you the inside story. And it says they met by chance, got hooked on an idea, and wrote the Transformers paper, the most consequential tech breakthrough in recent history. Now, the reason why transformer architecture is potentially so powerful is that it's a very scalable architecture that can be trained on very huge amounts of data and can be made to be very large and complex models. Now, I guess a lot of the reason why this transformer architecture and these foundation models have gotten so much attention is because at the end of 2022, we had the release of ChatGPT from OpenAI. And ChatGPT is an example of a large language model. And I guess everybody is using these systems now. And shortly after that, we had the first papers being published in all medical specialties looking at it. I think one of the first papers in ophthalmology was published in Ophthalmology Science at the start of 2023. And this was led by an up-and-coming ophthalmologist and researcher called Faraz Antaki. Faraz is a Syrian-Canadian ophthalmologist, and he's just actually finishing a year with me working in London before in the process of moving to the US to do his vitreoretinal surgical fellowship in the Cleveland Clinic. So in any event, he published this paper at the start of 2023, just after ChatGPT became available. And in this paper, he was able to show that ChatGPT was able to get about a 60% score on the American Academy of Ophthalmology, ophthalmology questions. And this was without any fine-tuning whatsoever. So this was a pretty impressive result. However, what was really more impressive than that was that Faraz followed up with a second paper towards the end of 2023, this time in the British Journal of Ophthalmology. And in that paper, he showed the newer version of ChatGPT, which uses the GPT-4 model, and was able to show that model was able to get about a 75% accuracy in these AAO tests. And that was pretty impressive because that's, on par with or perhaps even slightly better than the performance of human experts on some of these tests. Now, a key aspect of these foundation models is that they can be trained on language, they can be trained on images, or they can be trained on a combination of different modalities. And so we're starting to see also what are called vision language models. And I'd like to tell you about one of the most exciting examples of these. And so this is something called Elixir. And Elixir has been released as a preprint in 2023. This is from the Google team. And this is a vision language model for chest X-ray interpretation. So essentially what they do with these vision language models is they train a model on images, they train a model on large amounts of text, and they essentially generate these feature representations for the images and for the text. And then they try and align those in high dimensional space and then link them onto a pre-existing large language model. And when they do that, it potentially opens up a much better performance in medical image classification and segmentation tasks, but it also opens up a range of novel applications. And so one of those is called visual question answering. And so essentially what you could do, and they show this in the paper, you could get a chest X-ray or any other medical image really, and you could upload it, and then you can interact with the model via language. So you might say, is pulmonary edema present in this image? And it says yes. And then you might say, where is the edema present? And it says bilateral. And then you might say, what's the severity of the edema that's present? And so you could easily imagine this being used in the context of a color fundus photograph or an OCT. You upload a retinal photograph and you say, is this normal? Yes or no. If it's abnormal, where is the abnormality? What is the disease feature? Is this mild, moderate, or severe? What other diagnostic tests should I do? What is the visual prognosis, etc.? What is the risk to the other eye? And on and on. And so it'll be really interesting to see these models start to emerge in ophthalmology and in other medical specialties. Now, another big feature of these foundation models is that they're also commonly referred to as generative AI, because they're not just good at doing things like classification and predicting text and answering questions. They're also able to generate text and generate images and generate other forms of data. And so for the last year or two, people have been looking at text to image generation, things like DALL-E. But what's been particularly exciting in the last just few months is to see that OpenAI have something called Sora. And I think Sora is the Japanese for sky. And this model is not publicly available, but you can go to the website and see lots and lots of examples. And the idea is that you can put in text and use that to generate a video. So one of the examples that I got from the website is someone types in photorealistic close-up video of two pirate ships battling each other as they sail inside a cup of coffee. And so pretty amazing that Sora then is able to generate a video like this with just a text prompt. And so think about what are the implications of that for the creative industries. Is it a good thing? Is it a bad thing? And how could this type of technology be used in a medical setting or in an ophthalmic setting, for example? Now, our own work in this space is because essentially we created one of the first foundation models in medicine, and we think the first in ophthalmology, and that's called RetFound, for Retinal Foundation. And so the idea of RetFound is that we got a large amount of data at Moorfields, which we call our MIDAS dataset, which is predominantly a diabetic retinopathy dataset. We combined it with some public images, and essentially we had about 1.6 million unlabeled retinal images, mixture between OCT, B scans, and color fundus photographs. And essentially we performed self-supervised learning on those scans to create this foundation model that we called RetFound. And then what we're able to show is that with just a small amount of labeled data, across a range of 10 or more different downstream clinical tasks, we're able to see very good performance. So we were able to fine-tune RetFound for things like diabetic retinopathy on color fundus photographs, or possible glaucoma, or predicting conversion from dry to wet AMD, or even a range of novel tasks like predicting stroke, predicting heart failure, predicting Parkinson's, and so on and so forth. Now, one of the nice things about this work is that we showed that we had performance that was better than other state-of-the-art approaches, but we also showed that our performance was more generalizable on external validation. We also showed that the approach is much more label efficient. So effectively, you were able to fine-tune it on tasks where you might not have a lot of labeled data. And so we think that that's important because it opens up the possibility of looking at less common ophthalmic diseases. So up to now, we've mainly been focusing on things like diabetic retinopathy because we have a lot of data. But what about retinal genetic diseases? What about uveitis? What about ocular oncology? And so on. And then the last key feature was that we were able to show that it was fairer across different ethnic groups. And so it maintained its performance, whether it was in Black British or Black Asian patients and the diverse ethnicities that we see in Moorfields. So in any event, we've been working on this for the last year or two, and so it was very exciting then in September 2023 that we were able to publish this and publish it in the scientific journal Nature. Now, one of the other things that we felt, I think, quite proud of is that we have made the model code and the model weights open source for non-commercial purposes with the paper. And so that's cool because we think that, or we hope that others will be able to use what we've done as a cornerstone for their efforts to develop these AI systems. So for example, if you're an AI researcher in Poland, you might want to take our pre-trained model and then fine-tune it for an application using Polish data. So you might be developing a Polish diabetic retinopathy tool, or you might be developing a Brazilian glaucoma tool. And we hope that what we can do can almost be like a base camp for you to help you kind of climb the mountain of being able to develop these systems. Now, the other thing that we've seen is that there's some early evidence of this tool being used by others since we made it available last September. It was exciting then just before ARVO this year that there was a paper published in NPJ Digital Medicine, and essentially this was a group from China, and what they were able to do was to take our pre-trained version of RetFand, and they were able to fine-tune it for diabetic retinopathy screening in their own local population. And just to highlight a couple of the key results there. So the first was that using RetFand and using it fine-tuned for their population, that it had a much better sensitivity and specificity. In fact, over 15% better compared with some commercially available diabetic retinopathy screening tools in a Chinese population. They showed also that it had better generalization ability than some AI techniques developed using convolutional neural networks. And then they also did a decision curve analysis, indicating that this would have a higher net benefit in community-based screening. So for us, it was very exciting to begin to see others using our technology. Now, in terms of the next steps with this, well, we're exploring a number of different applications with local fine-tuning. So we're exploring collaborations with a number of low and middle income countries to see if we can fine-tune RetFand to, have more locally effective models. We're also working on increasing multimodality. So we have got a version of RetFand called RetFand M, which essentially now has been trained on about 6.8 million images from 14 different retinal imaging modalities. And so we think that having a truly multimodal model could be quite powerful for a number of reasons in the future. We're working on developing a three-dimensional version of RetFand because the version that I've just described that we published last year, that actually only works on OCTP scans and not the full OCT volumes. And we think actually, particularly in a field like oculomics, to take advantage of this technology, we really need to use volumetric scans. We're also trying to scale up RetFand. We have more than 20 million images in our database at Moorfields. And so we're interested in what happens when we scale up the amount of data that's used, when we scale up the model size, scale up the model complexity, do we start to see emergent capabilities? And then one of the things that's fun to speculate about is you know, what happens when we go to 100 million images and beyond? And how do we get there? Can we use things like synthetic data? Can we use new technologies such as federated learning to begin to allow us to get to that level of data? So to the point where we might be able to see these emergent capabilities that we've seen outside healthcare with these foundation models. And then the other thing we're already thinking about is vision language models and how we can get those. So just before I finish up, there's a couple of other things I just want to highlight, just to flag to you. The first is, I think we're seeing real advances in synthetic data. And so there's a very nice preprint from a group in China where they use something called diffusion models. And essentially they can take these diffusion models, if you look there in the top left, they can get real retinal images. And so what they've done in this preprint, they got about 150,000 real retinal images. They used a diffusion model to create about 1 million synthetic retinal images. And then they trained a classifier on top of that. And what they claim in this paper, and hasn't been published yet in a peer-reviewed journal, is that they get performance on par with the performance that we got with RetFound, but using this mixture of real and synthetic data. And so we're very excited about this because maybe that will, for the first time, allow us to much more easily share data, much more easily train models on huge amounts of data, and begin to see these emergent capabilities. Now, the other thing related to that is I think that we're going to see some paradigm shifts in the use of data around something called federated learning. And just to flag that I work with a startup in London called Bitfound that are specialists in federated learning and other privacy protecting technologies. They're founded by a guy called Blaise Thompson, and Blaise was previously the chief architect for Siri at Apple. And one of the things that you might not know about Apple is that they're a leader in federated learning. And when you have your iPhone charging by your bedside at night, Apple will train its AI models on data from millions of iPhones every night, but the data doesn't leave the iPhone. Instead, they actually send the models to be updated to the iPhone, and this is using this technique called federated learning. And so it's been exciting to be able to work with them. They're based just 5 minutes walk away from Moorfields. You can see me hiding at the back there on the right. The guy on his knees there at the front is Matt Siegel, and he was actually the person who built the federated learning network that Apple uses in millions of its iPhones. So it'll be interesting to see how that begins to be adopted in medical and ophthalmology settings in the future, and how it links in with foundation models. So, you know, as I like to finish pretty much all my slides, you know, I hope that I've begun to convince you with this work that we've got a technology like the slit lamp that's more than 100 years old, hasn't really changed much in that time, but we're on the cusp of reinventing ophthalmology for the 21st century using AI. And I think that this technology of foundation models is going to be central to it in the coming years. As promised, that's my email address. That's it for me. Thank you very much.
Dear colleagues, now we can start the discussion. Two of the speakers are with us. I see Siamak. Hello. Good to see you. Thank you for being with us. And I see Kai, well, is logged, but for any reason.
Hello. I'm here.
Okay, you are here. We cannot see you, but we can speak. I mean, okay.
Yes.
Unfortunately, Professor Piers Skinner, for any reason, is not with us, but we can start a discussion, and the chat is the place where you can put your questions to our speakers, at least two speakers, because to Professor Skinner, you need to probably write the questions to him. He shared his email, and so it's relatively easy to contact him. He's very communicating very well. Okay, so we got the one question, Siamak, to you, I think. Yeah, would you like to address it?
Sure. Yes. So yeah, the very first question to me. So can you hear me well first?
Yeah.
Okay, perfect. So this is a question regarding the OATS dataset with over 40,000 fundus images. So let me just, again, get back to the OATS. Again, OATS stands for Ocular Hypertensive Treatment Study. It was conducted back in 1991. It's a very long longitudinal clinical trial. May Gordon and Michael Cass actually were two primary PIs for this data set. Both of them are at WashU, Washington University in St. Louis. I reached them out at the time. This is, the story of back in 2018. And through a number of email communications, signing the data agreements and all of these, we ultimately got access to the data. But last year in Arvo, I heard from Dr. Gordon that she is working with dbGaP. Some of you may are already familiar with dbGaP. It is I think it is for NIH. NIH supports that. But anyway, they are going to put it there, and then people can ask for the data set, sign the data agreement, and likely pay, something. At the time we paid for it, and then get access to the data. So this is not the short answer, that this is not publicly available right now, but it could become available if you reach them out and then sign some data agreement and data use agreements.
Thank you. Well, of course, if you have any questions to each other, well, welcome to do that. Presenters. But let me start, because we will focus probably now on the large language models. Well, we all were probably impressed by introduction of ChatGPT and potential possibilities. But then I quickly realized that we are in the sort of the transition period, what means that every version is better than the previous one. Then, as you mentioned, Siamak, commercial access is better than the free open access. And then, of course, there's a competition between different now models. What will be and I can add, as an editor of many journals, that I faced enormous number of papers related to ChatGPT or any other LLM model that were submitted recently to journals, sometimes not giving any additional knowledge. Just people got crazy about that completely. Also in the research, and then maybe we should wait a little bit. For the final, because before we introduce something to the healthcare, we need to be really sure that we achieved a very high level. And of course, we are also quite aware about some problems with the large language models. There were that we cannot control it completely. That the of course, I don't. This is symbolized sometimes as hallucinations and so on. So, what do you would comment on that, Siamak, please? Are we really in the transition, or shall we wait for the future level, or be based on the present, let's say, quality of the model?
So that was a great point. I also explained that when we started working on these large language models, we previously were working on Albors, the humanoid robot, and it was also equipped with some levels of natural language processing. But it was natural language processing. It was not the NLP that these recent LLMs are equipped with. So when ChatGPT was introduced, as one tool that stands out among all the others, we just realized that, most of the things that we want to do with Albors, now LLMs like ChatGPT can do it. So we also transitioned to that. And I totally agree with you that, because it's a hot area, right? So then we said, okay, let's work on LLMs and then try to see that how they perform, how we can address different problems using LLMs. But we approached the problem from two different angles. At the time that we were working on this, that was mid or early last year, actually 2023. We started working on large language models. We just said that, okay, so now some of the people are working on case reports. Let's also us working on case reports as well. So at different, I mean, ocular conditions like a cornea, like glaucoma, and then neuro-ophthalmology, 3 different areas. And then we said that, okay, so this is great, but this is not enough. Why? Because most of the publications that we saw in ophthalmology were on a very limited number of case reports, including us. I mean, then we said that, okay, so is it possible to work on OATS, for example, from the tabular data? So these are the, I mean, parameters in the Excel files I'm talking about. Then we said that, okay, is it possible to turn these tabular data first to case report and then from case report to prompt and then use ChatGPT and these 4? Then because this was a larger data set, then it was more dependable. I mean, having 1,600 cases for sure is much more, I mean, the outcome is much more dependable than a few, for example, hundreds or just, I mean, tens of samples. So that's why we just work on 2 other studies based on the OATS dataset as well. But I totally agree with you. So at the time, or even just, I mean, over the past few months, we have seen a lot of progress in the ChatGPT. Even the commercial versions, the new versions comes, and the new versions are equipped with, I mean, a lot of other capabilities. For example, multimodality. This is something that we are very interested in, and I believe if ChatGPT is going to be successful, it's at this direction. Multimodality means that being able to analyze images, fundus, for example, just fundus images, visual fields, and then the clinical parameters. But what we learned is that ChatGPT, based on textual data only, it has a limit on accuracy. And as I mentioned, I mean, the area under Darcy was, I mean, something close to 0. For example, 75, 76, 77. But if they can really interpret fundus photographs, I mean, they can, for example, work on Coptis ratio with a good accuracy, not just, I mean, an estimation that is far from the reality. They can be very helpful, and they can also be integrated at that level. So to answer your question shortly, I believe if we can get a multimodal large language model with a great accuracy, then that's the target that we can work on, and then we can show the community that, hey, this is something that we can use, and these are the outcome of, I mean, that model.
Thank you so much, and I must congratulate you. The recent paper in American Journal of Ophthalmology, you referred to this data in your lecture. For those who did not read it yet, please do that. I mean, this is very interesting. Application of the ChatGPT for glaucoma prediction. And by the way, when I read this paper, it appeared, I think, several weeks, maybe 4 weeks ago, something like that. It was just before European Glaucoma Society meeting. I was invited to deliver a talk on AI. I use this to show a very recent, I refer to your work, recent developments in this area.
Great.
So, well, you also mentioned about, this is very interesting point, the prompt engineering, prompt, I would say quality. So depending on the, let's say, how you create a prompt, you can receive of different quality of the answer. So how people should at first learn, and then how to differentiate between bad and good prompts.
Yeah, that's a great question. As I said, I mean, now this is a very focused area. Even some of the people go and study, I mean, prompt engineering, because this is now very important, how you articulate the question. Actually, this is true for the human as well. I mean, if we ask a question, I mean, in just pretty much, I mean, different styles, we may get, I mean, different responses, right? In communications as well. So the same thing exists for these large language models as well. But the approach that we did had 2, I mean, major components. The first one, we said, okay, let's go and try to see that what are the major principles that we can use and we can learn for prompt engineering, and those are out there. We can just Google and check, and there are, I mean, some documents and papers regarding that. And then the second thing was that, okay, so now let's just pick, I mean, and select a subset of the data that is, I mean, easier to handle and quicker to analyze. For example, 20% of the entire OATS data set, because as I said, it was 3,200 eyes. So then this is a small. Now let's just engineer different type of prompts and then apply it on this 20% of the data and then see the outcome. So it was pretty much like machine learning approaches that we pick a subset of parameters and then see the outcome and then optimize this subset. So pretty much we use the same style of trial and error, checking, I mean, different prompts, and then ultimately running the pipeline that we come up with on the entire data set. But prompt engineering, as you also emphasized, is very important and very critical. Different questions can end up with different answers and different responses from these LLMs.
Thank you, Siamak. I have one more question. I mean, this topic, as a matter of fact, appeared both in your talk and Pierce. The problem of the explainability. I mean, generally, I mean, deep learning. It's a one of the limitation of different models. May large language models can be used to help us to explain better, to understand better the functioning of other models, or
yeah,
what do you think about this idea? I mean, to use large language models to increase explainability. Yeah.
That's, I mean, yeah, that's a great point. So yes, I think so. I mean, still the problem of explainability is a major challenge. And I mean, as a physician, you know that, right? You absolutely trust a model that can give you the reasons why I'm making this decision, compared to a model that tells you that, okay, yes, no, and there's no explanation. I mean, this is, I mean, human, and the physicians and even patients. I mean, even patients typically trust better when they know the reason why this is the, I mean, this is the outcome. So this is a fact. And still, we don't have a good and I mean, reasonable solution for that. I mean, there are a number of ways. For example, class activation maps, gradient-based class activation maps, a number of variations of these that can tell you some glimpse of what's going on, but these are not precise. These are not very high resolution. So anyways, yes, the answer is yes. I mean, large language models, and even large language models, assume that you have a large language model, you apply it on a fundus photograph. If it just tells you that this is glaucoma, you have the option that, why do you think that this is glaucoma? So for sure, it just gets back to you, right, with another response. So these, I mean, from this perspective, for sure, they are more explainable. And I think the best advantage of LLMs compared to previous CNN or transformer-based models are exactly this point, that you can interact with them and you can understand with them, you can speak with them. This is what I exactly told about Albor, is that this is a very, I mean, so yeah, there are a number of advantages, but to me, this is the best thing, that, I mean, it's like a human. You can talk with them, they can talk with you, and this is the way that we have communicated, I mean, throughout our life. So we understand that. And the other thing about the LLMs, maybe not related to your question, but let me just, I mean, just highlight this as well, is that they are readily available. You don't need to install anything. You don't need to know anything about, for example, installing a CNN model. I mean, you're making it first a standalone software, then installing, then learn how to work with it. And you can readily, I mean, it's on your iPhone, it's on your laptop. You can easily work with it. Even the kids can work with it. My dad can work with it. Everyone can work with it. So this is, I mean, this is another major advantage of these LLMs, and that's why I say that if they become multimodal with high accuracy, then this is both promising and also scary. Andrew. So then I mean, what my lab should do, if they can do the multimodal and they are highly accurate, pretty much, I mean, everyone can use those, right? And then, I mean, what we should do. So this is, I mean, as I said, both promising, great, and at the same time, I mean, a bit scary.
Yeah, thank you, Siam. I completely agree with you, and also with that one of the major achievements of OpenAI, for example, was not to make a model, because finally large language model. Well, this is the it shows that we need to finish. Where they were, I would say, already prepared before, and scientists worked for many years on these models. But the major achievement was to make it available for everybody. I mean, and it started a completely new era when people could have a contact, not only professional scientists, computer scientists, some of them have access, could work on that, but now everybody can have access. So this is in my opinion, it is the major breakthrough.
Yeah, absolutely right.
Thank you, Samak, so much for great discussion, for being with us. Kai, good to that we have any comment you want to add anything, or?
I think congratulations for the great meeting. Can I ask one question with the Professor Youssef?
Sure.
Yes.
Yes, please, go ahead.
Actually, we are working on the vision language large model from our team. So, based on your experience, at least how large a data set is required to establish a useful ophthalmic visual language large model? Do you have the experience?
So Kai, that's a great question, but there's no, I mean, a single answer to this. I mean, the overall response could be the larger, the better. But typically, I mean, for myself, based on different, for example, if we have a CNN, I say that it should be over 1,000. If it's multimodal, over a few thousand. But I mean, it totally depends. If it's a classical machine learning, even a few hundred, or I mean, a statistical model, maybe few tens, even just enough for doing a test or for doing a comparison. But the larger, the better. Over 1,000, typically more dependable. I mean, if I want to give you a number, but for sure, I mean, just Pierce mentioned about the foundation model, and then I mean, millions of samples, right? That these models are just trained based on. So the field also is just, I mean, transitioning to larger number of samples for various applications.
Yeah, I agree.
Thank you.
Yes.
Sure.
Thank you so much.
Thank you, speakers and colleagues. And now we will have a short break, and we'll meet at the second session. Thank you.
Thank you so much, Anzid, for having me. Thank you.
Good afternoon. I would like to thank Professor Jaworski for the kind invitation. My name is Hao Yichun from Joint Shantou International Eye Center, Shantou University, and the Chinese University of Hong Kong, China. Today, I would like to present a topic on clinician-driven automatic label noise cleaning for multimodal retinal imaging. So as we know, retinal disease are very important as they are the leading causes of blindness. And ophthalmic artificial intelligence is a very hot topic recently. And in the ophthalmic artificial intelligence, color fundus photo and OCT are the most common use modality for the screening of retinal diseases. The quality of data is very important. It's the fundamental of the artificial intelligence model development. For example, there's you can see that if we have accurate data, then we can get an accurate decision. If we have a wrong data, then we may get a wrong decision. And it is said that garbage in and garbage out. If we train the model with some bad data, some data with noise, then we can not get a good model. So it is very important to ensure that the quality of data is good enough. And there are some data noise that may come from two aspects. The first one is the image, and the second one is the labeling. The image, some image may be very difficult to diagnosis or difficult to grade. And for labeling, there's also some noise because it is a subjective. It is a very subjective process, and also there may be some inconsistent between the two different grader or even in the intergrader, there may be some inconsistent. For example, if I grade this image 2 weeks later, I may put on a different label. And so it is reported that the noise in the mainstream data set are very high. It ranges from 3% to 38%, almost 40%. And medical data is very medical data set is very important for development of the AI model, and some public data set are very common and repeated use. For example, for the iPad dataset or the APTOS dataset, they are very common use. For example, they have so many usage here, and there's maybe some noise in the labeling. For example, this one, it is the original label is MPDR grade 1. However, it should be MPDR grade 2 if we look at it carefully. And this image from APTOS was original graded as MPDR grade 3, but actually it is a PDR. And so the annotation of this image is very time consuming and label intensive, and it is also very easy to make mistake. There's some noise inside in the data set, and it is very important to seek automatic label cleaning measures for this large scale data set, and because it is very difficult to clean it manually. So to manage the data set with noise, there's several different strategies. The first one is noise learning. That means that the model can learn with the label noise. The second one is confidential learning. It is this method is to find out the error of the labeling. And CleanLab is a framework based on confident learning, and there's several advantages. The first one, it is fully automatic, and it is user friendly, and it is open source and not strongly coupled with data or model, and it is highly compatible. It can be used in text, table and image, and it is widely used in natural image tasks and show good performance. However, it is unknown for the whether this CleanLab is good in ophthalmic imaging and whether there is some risk if we use this framework in the ophthalmic image. So the purpose today is to assess the efficiency and potential risk of CleanLab in automatic rectifying label error in color fundus photo and OCT dataset, and to assess whether the data cleaning improved the performance of deep learning model in the classification of retinal imaging, and to explore a strategy to optimize the number of the cleaning iterations. So we developed these two datasets. The first one is a color fundus photo dataset, and the second one is the OCT dataset from our data, and all the data are identified. And for the color fundus photo, we have this A category, and there are 200 images in each category. So we have 1600 images for the experiment, and we also collect another other 20 images for each category for the testing. And for OCT, we have seven categories, and we have 140 slides in each category, and totally we have 980 images for the experiment. And we also collect additionally 20 images for the testing for each category, and the annotation is performed blindly and independently by two ophthalmologists, and only the consistent result were included. Then we perform this pseudo label noise strategy. So we inject noise into the dataset, and we set 15 gradients and with 5% noise rate, and we sampling for 3 times. For example, we randomly put some arrow labeling into 5% of the image. So there's the 5% noise, and then we increase this rate into 10%, 15% until 70%, and then we perform this CleanLab cleaning on our service and with these parameters, and also we test our model, our data with a RedFarm pre-training foundation model to classify the image. We use this metrics to assess the performance of the automatic cleaning method, including the accuracy, the label issue rate, detection rate, miss rate, correct modification rate, error modification rate, precision, recall, and advanced score. So this is the result. So we can see that before cleaning, we have this data set in here, and then after 6 rounds of the cleaning, then we can see that the number of the correct labeling increased. And this is the confusion matrix of the two examples. For this one is a 40% noise rate of color fundus photo and 40% noise rate of the OCT. You can see that the original confusion matrix, we can see that there's many mistake here, error labeling here, and after the first round of cleaning, we can see most of the label noise is gone, and it keep improved with the second, third, fourth, fifth, and sixth round of cleaning. And for the OCT, we can see the same result. That after the first round of cleaning, we can see most label mistake, label error is gone, and it improved with the additional iteration of the cleaning. So if we quantify the result here, that this is the label accuracy, we can see that this is several different original data set with different rate of the label noise. So you can see that it improved a lot within the first round, and then keep increasing until the sixth round in both color funded photography and OCT. However, we also note that the data set, original data set without any noise, the accuracy decreased after the cleaning here. And also in this 5% noise rate data set here, we can see that it increased at first but decreased a little bit later on. And the CleanLab framework, it can also automatically calculate the dataset quality score. We can also see that the dataset quality score it has very similar pattern with the label accuracy, and it increased significantly with the first iteration of cleaning, and then keep improving, but not in this original dataset of the without any noise. So is there any risk for this automatic cleaning? Then we can see that this is the noise rate here, and this is the accuracy, and this is the correct modification rate. We can see that most of the label noise is correctly modified, and the maximum number is 97%, but the lowest one is 92%. And we can see that there are also some error modification sample. The maximum rate is maximum number of the error modification is about 6%, and there also about maximally there are 2% are missed during the automatic cleaning, and also there are about the maximum number of the false labeling is about 5%, and the same for the OCT dataset. The OCT dataset may be a little bit higher, but a similar pattern. So we can see that we have a very high correct modification rate and low error modification rate and miss rate. So we can make a conclusion that the risk is low for this automatic cleaning method. And the next question is how many iterations are needed. So we at first we use this 6 iteration, and we need so many iterations, and we can also see that some data set without any noise, if we have too many iteration, that the performance, the accuracy of the data set decrease. So we then investigate that the optimal number of iteration. So we perform this correlation analysis of the dataset quality score and the label accuracy. We can find that they have a very good correlation, and then we calculate the AUC curve, and then we calculate the cutoff value for the dataset quality. We can see that the dataset quality is, for example, the dataset quality of the color funded photo is 0.9965, and for the OCT is 0.9925. That is good enough. So if the quality score reach this number, then we should stop the iteration. Then we can analyze the number of the iteration with the noise rate, then we can see that it also have a good positive correlation. That means that the higher noise rate of the data set, the larger number of the cleaning iteration is needed. So this is the result of the comparison or classification accuracy. So we can see that after the cleaning, then we can see that the classification accuracy improved, especially in the higher noise rate data set. For example, in this 70% noise rate data set, that the initial classification accuracy is about only 0.66 and improved to 0.87. And we can also see that in the original clean data set, for example, in this 0% noise rate, that the accuracy is 0.94, and it decreased after the 6-round iteration cleaning, but for the dataset quality guided strategy, that it keep the original high accuracy, and it's the same for the OCT datasets. So this is the summarized result of our result. That for example, the red color means that the accuracy. So the original accuracy, dataset accuracy is here, and after this iteration, we can see the input to this dark red color here. And for the dataset quality score, before cleaning, it is the light green here, and then it improved to this dark green after the cleaning. And also we can see this blue one is the classification accuracy, means that if we use the red farm to classify the retinal diseases based on the dataset before and after the training, we can also see that after the cleaning, then that the accuracy of the classification improved, especially in this dataset with a high noise rate. So and we can see that it is this result is also found in OCT dataset and also in this dataset quality score guided strategy. That it means that we don't use 6 iteration. We use the optimal number of iteration developed in our last slide. And we also apply this strategy to the public dataset. We apply this CleanLab to the APTOS and IPEX. We can see that after the cleaning, that the accuracy of the dataset increased from the 0.6 to 0.92, and for the iPad it also increased for the accuracy of the dataset. So this study is the first one to apply a general automatic label cleaning to ophthalmic imaging, and we can find that the label noise can decrease the performance of the artificial intelligence model and also increase the clinical risk. And the label cleaning can improve the label accuracy, dataset quality score, and the model classification accuracy. And the risk of CleanLab is low because we have a low miss rate, error modification rate, and false labeling rate. And excessive norm of cleaning may decrease the performance a little bit, but so the dataset quality score guided strategy can prevent the excessive cleaning and also can optimize the dataset quality and also dataset accuracy and also classification accuracy. And because we use these two different modality, and so we can conclude that this method can be applied to other medical image. And also, and finally, we conclude that CleanLab is efficient and low-risk methods in correcting the label error and enhancing data set quality and increase AI performance in multimodality retinal imaging. Thank you very much for the listening.
Dear colleagues, this is my pleasure to speak today on some updates on AI for diabetic retinopathy screening. Next slide, please. This talk is sponsored by the Viatris company, but the company had no influence on the content of this presentation. Here are my financial disclosures. None of them is relevant to the topic of this presentation. Next slide, please. Yeah, we are quite aware about the increase of the, let's say, literature studies on AI in ophthalmology in recent years. What is presented at this graph, as you see, especially at the end on the right side of this graph, between 2016, 17, up to date, the number of publications on AI in ophthalmology is much higher than 1,000 per year. So it's really number beyond the capacity of any person to read well, all of these papers. Next slide, please. And even AI is used in every subfield of ophthalmology, I would say today. There are some subfields, they are, let's say, more active and more often approached. And there's certainly number one in ophthalmology is diabetic retinopathy, as you see on the left side, and glaucoma as a second subject, AMD as the third subject. Next slide, please. A lot you can find in our textbook that was already published a few years ago, Artificial Intelligence in Ophthalmology, and there is a chapter on diabetic retinopathy there, and there is a recent publication from last year, free available from internet. This is open access publication, so please find more information here. And the book, let me add, was just recently translated into Chinese. We have the Chinese edition in May this year. Next slide, please. So why diabetic retinopathy became such a, let's say, successful area for AI development in ophthalmology? Well, there are several reasons for that. One is certainly epidemiology. So we have a lot of diabetic patients, diabetic people in every population, and diabetic retinopathy is also a relatively common disorder. As you can see, this is the data from Poland. We have around the population of 38 million of people, and around 3 million people with diabetes, and around 1/3 there are people with diabetic retinopathy. So around 1 million of Polish citizens, they have diabetic retinopathy. However, we want to reach people with vision-threatening diabetic retinopathy. This is around, again, 200,000. So at first, epidemiologically, it's a common disorder. Secondly, we have a subpopulation, so it's always easier to do a screening within the subpopulation. In this case, this is the subpopulation of diabetic patients. This is not, unfortunately, the case with other ophthalmic disorders like AMD or glaucoma. Next slide, please. Another reason why diabetic retinopathy AI-based devices became so successful is that the retinal lesions that we can see here on the fundus picture are well understood and well described. So they are relatively easy to be graded, to be annotated, as it is shown here. What is very important for AI training. Next slide, please. Another issue is that we do have a clear, let's say, staging for diabetic retinopathy between non-proliferative and proliferative. Next slide, please. And also a clear classification that is very important for every training in every sort of disease, as you see here. Next slide, please. Here I would like to refer to the recent publication by our colleague Ryo Kawasaki from Japan, who this was published this year, this publication is about how can artificial intelligence be implemented effectively in diabetic retinopathy screening in Japan, but it also can be used for any place all over the world. So just to mention about some interesting information within this publication. So in this table, we can see features of organized or systematic screening that are relevant to diabetic retinopathy screening. Number one, this disease to be screened for is important and a frequent disease, and this is completely fulfilled for diabetic retinopathy. Number two, the disease can be easily diagnosed by non-invasive methods. Again, it's true for diabetic retinopathy. Prevention, treatment, and rehabilitation methods are, after diagnosis have been established, again, we can confirm that. And early detection by screening leads to effective treatment after diagnosis and cost effective. So again, it is very true for diabetic retinopathy. Next slide, please. Here we see the table 2 from the same paper showing 4 stages to develop systematic screening of diabetic retinopathy. So as you see, the first stage, enhance access to effective diabetic retinopathy treatment. The stage 2, establish opportunistic screening. Stage 3, establish systematic screening, and stage 4, establishment of a systematic screening with complete quality assurance and coverage. Next slide, please. This graph shows different applications of AI and diabetic retinopathy and diabetic macular edema. This is again from this paper that was just recently published. And as you see, it includes diagnosis and screening, staging and classification, lesion analysis, functional assessment, personalized treatment planning, and finally, progression prediction. Next slide, please. Here we can see the table presenting AI-based devices that were available at the European Union last year. This is the table from our paper that we published last year, as you see in April. So it was submitted a few months earlier, and this is the picture for that time. However, next slide, please. It changed much, and here this is the draft of the table we prepare now for the update. It is not finalized. Next slide, please. But just to show that this number of these AI-based devices for diabetic retinopathy roughly doubled. So we have just during 1 year. So it shows a huge progress and development in the number, at least, of the algorithms and companies and so on. Next slide, please. This table, again, from very recent paper published in Graph's Archives, presents different models and different methodology that was used to detect, classify diabetic retinopathy. As you see, I will not discuss all of them, but well, just to show a diversity of approaches in this particular field. Next slide, please. Here it's a very interesting study that was also published recently, and it showed, as a matter of fact, it analyzed the effectiveness of AI screening in preventing vision loss from diabetes, and it shows that autonomous AI is expected to be more effective than eye care provider-based screening at preventing vision loss among patients with diabetes. It can be maximized by improving processes of care, particularly adherence with recommended treatments. And they shown that introducing AI in no diabetic retinopathy disease screening scenario is estimated to be over 8 times more effective at preventing vision loss from diabetic retinopathy compared with introducing eye care provider-based screening. Next slide, please. And this is the graph from this study showing, as you see, this highest bars in the middle, the largest impact on vision loss is estimated to be from maximizing adherence with ophthalmic treatment, followed by adherence with metabolic treatment. Next slide, please. This is another interesting paper that was recently published last year in JAMA Ophthalmology, and this study shown that it was possible by using AI model to estimate best corrected visual acuity directly from fundus photographs in patients with the DME, so diabetic macular edema, without refraction or subjective visual acuity measurements, often within 1 to 2 lines on an ETDRS chart, supporting this AI concept if additional improvements in estimates can be achieved. Next slide, please. However, the editorial that accompanied this article by our colleague Sally Baxter pointed that 40% of AI predicted best corrected visual acuity were more than 10 letters different than the protocol measured BCVA, and the role of this AI algorithm needs further validation. Next slide, please. This is a figure from another very interesting study that was published beginning of this year in the Nature Medicine. In this case, a deep learning model was used to predict time to progression of diabetic retinopathy. Next slide, please. And they shown that the as you see on the left side and the lower part of this graph, that the feature contribution was highest from fundus score, then glycosylated hemoglobin, and duration of diabetes, body mass index, smoking status, and so on. Next slide, please. And they shown also, this is let's say, the second column of this table, reduction in screening frequency, that by using this model, they were able to significantly, as you see, reduce the screening frequency by roughly 60%. Next slide, please. Another study that was already discussed today by Professor P. Skinner, well known as paper using well, the first foundation model in ophthalmology, just to mention that it was also used for ocular or for diabetic retinopathy diagnosis. Next slide, please. This is also quite interesting study by Paulo Silva group that was published last year. And this study, they compared a customized auto machine learning model with the FDA-approved systems, and they shown very high, very good performance of this auto ML model when compared to IDX or INUC. Next slide, please. This is also a quite interesting study by colleagues from Google who shown that using external photographs, not only fundus pictures of the eyes, we can train the algorithm to detect diabetic macular edema, to evaluate hemoglobin, glycosylated hemoglobin level, and also serum lipids. Next slide, please. Well, we also know that very often reality is far from the expectations. So we need also to shortly discuss some problems and limitations related with the AI, at least, well, in the diabetic retinopathy field. Next slide, please. So one of these examples is the Google's algorithm that was very accurate in the lab. However, in the real life, it became much less accurate, and it might happen finally to every algorithm. Next slide, please. There is increasing number of studies showing that within the huge quantity of studies that I presented at the beginning of this lecture, over 1,000 papers in AI and ophthalmology per year, we have majority of them are of relatively poor quality. This is a very interesting study that was published just recently in the Journal of Eye, as you see, and they analyzed different, 86 unique randomized controlled trials that were published in the period between 2018 and 2023. And they found that models reporting was insufficient in determining sample size and missing data treatment, that the full access to data sets at code was also underreported, that only 3% studies were classified as having a low risk of bias, whereas over nearly 97% were classified as having a high risk of bias. Only 16% of studies use prospective external validation cohorts. Only 6% describe the study calibration. Next slide, please. So we see here the studies were in the different subfields of medicine. However, the authors highlighted that for nearly 300 AI-enabled medical devices, FDA approved, only a few have undergone evaluation using randomized controlled trials. Next slide, please. And they also included, they shown only 3 ophthalmology-related RCTs, as you see them here. They were conducted in China, Rwanda, and Bangladesh, and 2 of them were on diabetic retinopathy screening. Next slide, please. Here we see the publications. These 3 ophthalmic studies within this analyzed group. Next slide, please. Another problem that is recently highlighted is the problem of the lack of transparency. So it is often shown that publicly available information for medical AI products and the European Union market does not meet transparency requirements to inform the public about safety and risks. Most products had no information on training data collection and population characteristics. Some products had no published results from validation studies. Next slide, please. So here I just try to summarize major limitations, problems with AI-based medical devices. As you can see, one of them is a lack of external validation of the systems, limited numbers of randomized clinical trials, preponderance of retrospective studies, heterogeneity in the metrics used that makes comparisons difficult, lack of availability of the data sets and codes. Next slide, please. Most AI algorithms tested are on the data sets not corresponding well to the real world conditions. So patients' populations are usually homogeneous. Poor quality images and patients with multiple pathologies are usually excluded, and there is often a conflict of interest. So great majority of the published papers are conducted by manufacturers and patent owners. Next slide, please. There is a lack of the direct comparison, head-to-head comparisons between algorithm and diabetic retinopathy subfield. This is one of a few examples. Is the study by Aaron Lee that was published already 3 years ago, well-known study, when they compared 7 algorithms from 5 different companies, and they found that the accuracy results varied significantly between the algorithms. Next slide, please. Here's our study. We also do such a comparison. This is a comparison between IDX retinalized. Next slide, please. And this is the comparison between IDX and the remedial system, the Indian algorithm, and more studies are coming. We just finished a study with the comparison IDX to Tirona and IDX to Mona and some other algorithms. Next slide, please. So coming to a conclusion, what is next? I think that the major problems now include the transparency, the lack of transparency, lack of explainability, and finally, openness for peer verification of the model that is prepared. Next slide, please. So at the end, I would like to conclude with a saying from very good book, Super Forecasting. If you do not get feedback, your confidence grows much faster than your accuracy. Thank you very much for your kind attention.
Hello, my name is Jan Wasilewski, and I am PhD student at the Rochester Institute of Technology. And today I will present the work I was doing while working at ENG, Poland. And the title of today's presentation is The Problem of a Small Number of Labeled Examples in the Diagnostics of Retinopathy Based on OCT Images. So it is the usage of artificial intelligence algorithm, in particular neural network, to help in diagnosis of retinopathy. The neural network, almost all of the artificial intelligence algorithms are predictive algorithms. So given the input, they produce the output based on the relationships that they've already seen, that they've already learned. So today I will address one problem linked with that training. We will start with the technical description, more or less technical. How does it work to visualize the problem? So in order to train neural network, we need data. So here you've got OCT images. For human beings, it looks like the grayscale image. Of course, it can have multiple layers. This image can have depth, but we see the image. The computer, however, sees the matrix. So these are just big matrices of numbers. Each pixel, each part of the image is a pixel. Each pixel has a number, and these numbers represent such the image to the computer. So this big matrix is then fed to the neural network. The neural network is presented as such a graph. We've got edges and nodes. So each pixel appears in the first layer. So these blue circles take input pixels as the input, and then process them through very simple mathematical operations such as multiplications. They multiply these values by the parameters, by the parameters called weights. So we do it multiple times, and in the end we are left with two green values. So from all of these pixels, we end up with the smaller number of numbers, and these numbers are normalized to present the probability distribution, and this probability distribution tells us what's the network's output. So for example, in this example, we've got 4 values in the end. Healthy, this is 1, this is 2, and this is 3, with probabilities. So that is how it works. But of course, that's the technical description. But how can it predict that this particular image is this is 1, and this particular image is the other image is this is 2. In order to achieve that, we need to train the neural network, and training process requires the crucial step. So from the beginning, we have the OCT image we fed to the neural network. Then the neural network multiplies and adds and multiplies and adds multiple times the pixel informations, the pixel values. And then we end up with the prediction. At the very beginning, this prediction is random. And the network doesn't know anything. So the crucial step is the comparison between the current neural network prediction and the true label. While we have the information about the true label, so if it is the healthy patient or the patient with a disease 1 or 2 or 3, we, based on that knowledge, we adjust the weights of the neural network. We do it multiple times. And after many images seen, the neural network learns how to correctly predict what is on the image. So the typical situation in practice is that we have thousands of unlabeled OCT images. However, only hundreds of labeled OCT images. So in other words, we've got the access to the very big corpus of unlabeled OCT images stored somewhere in the hospital or somewhere, and only a few labeled OCT images. And acquiring these labeled images requires a grader. So someone who will sit down and tell, okay, in this image I can see the healthy patient, and in this image there is disease 1 and also a disease 2, and so on. The business problem from that perspective is that the grader costs. Of course, it is not a pleasant activity to label images, to view them, and to produce these labels, especially while you have other things to do, such as saving human lives or human health. So having that problem in mind, at OKE Poland, we were developing this project and we were trying to address this issue. And we were attacking this issue by using active learning approach. So the active learning approach focuses on taking the most informative samples from the bunch of the unlabeled ones in order to save time and cost of the graders. So how does it work? We train neural network by comparing the prediction with the label. However, and then by this comparison, we adjust the weights. However, some of the examples give better information, so they steer our weights, our neural network to perform better, faster than other examples. And the task is to identify these examples, these images that will give us the most information. And to give them to graders, to give only them to graders, and to get rid of all the unnecessary examples that otherwise would have to be annotated by the physicians. So the crucial step is this selection process. How can we distinguish between informative and non-informative example? And we were trying many multiple of approaches. Here are the results for three very simple algorithms based on entropy of the prediction, the least confidence, and the marginal sample. As you can see in a graph on the left hand side of the slide, we score better than random instance selection. However, this boost in performance is not the huge one. But when we calculate the cost, every sample saved is $15, and we multiply it by hundreds. Of course, it is valid from the business perspective. So the random selection process is visualized here as a gray line in a plot, and the entropy algorithm, which is the best one from our experiments, trains the network faster. It is not the big difference, as I mentioned before, but of course, here, after the sixth batch, the number of batch is presented on the x-axis. We see the significant progress. So instead of 80% of the accuracy, with the same amount of labeled samples, we achieve 85% of the accuracy. And of course, it is very important because while this algorithm, when it helps the physician to diagnose, it cannot make mistakes. It is obvious. So, to sum up, models need labels during training. There is lots of unlabeled data, but only a little of labeled data. The next point is that labeling is very pricey. Therefore, we developed the active learning approach to minimize the grader costs and to train neural network faster with less data. So, in other words, we try to identify those informative samples, those informative images that will push our network to the correct predictions the most. On the other hand, it can also be seen from the medical point of view, from the medical science. Identifying the most informative samples might be beneficial from the medical science perspective in that sense that these are the most interesting examples. So at the very beginning, we will try to collect the most typical ones, and then the hardest ones. And identifying these hardest ones, of course, might serve as the good strategy to train human physicians as well. So that's it, and I would gladly take questions. Thank you very much.
Ladies and gentlemen, my name is Piotr Artieniev. I'm from University of Varna and Mazury in Olsztyn, Poland, and I would like to show you the following topic: predicting children's myopia risk, a Monte Carlo approach to compare the performance of machine learning models. This presentation will be by prism of information technology, because I'm a data scientist, and just machine learning models are my natural environments, natural topics. The plan of presentation is as follows. I would like to show the goal, the methodology, experimental part, and some conclusions and future work. Our main goal is to present some initial results of myopia risk calculator MRC consortium, and to show some machine learning approach to evaluate the problem of decision making in this particular topic. And the collaborating researchers in this consortium are as follows: researchers around the world from some universities and institutions. And let me outline the motivation. Basically, the working on a very important problem affecting children and wanting to help with prevention is the main motivation, and we can use actually the machine learning technology, machine learning models in many contexts, but this one is particularly important for us. And let me show you the general methodology we use. Actually, it's a crisp data mining framework, which consists of business understanding. In that case, define objects. We predict myopia risk in children based on some factors I will show later, and assess the potential impact of public health. Data understanding part. Here we use some provided data from Charlotte School Children Eye Cohort Study, and they use some initial data exploration to select the attributes and so on, and identify the key variables for myopia prediction. And in data preparation step, we clean data, handle missing values, handle some null values and outliers, transform data using some normalization, scale attributes, and do some feature engineering. And in modeling part, we use some exemplary models which as follows. It was logistic regression, KNN, support vector machine, and so on. A few models I will tell you in detail later. And we use basically we use train and test model, multiple train and test. We call it Monte Carlo approach. And additionally, the second variant of Monte Carlo approach is just random drawing of final results to obtain a huge number of possible results to define some percentiles of results in a more comprehensive way. And actually, In evaluation step, we do some evaluation computing some specific parameters, also detail later. And in last step of this methodology is, of course, the deployment. We are working on to create a web page to share tool, user-friendly tool for clinicians. And actually, the methodology in detail in the Monte Carlo plot, as I said, we use two basic methods. Actually, multiple random splitting in just bootstrapping technique. And another one is to collecting some results, for instance, having 1,000 values of accuracy or sensitivity, specificity, precision, and so on. We just, by random drawing, we collect some more results to have a huge number of results and compute based on them quarters of results. And actually, the data we use in our experimental session are data from 3,989 children from Shahrut School Children Eye Cohort Study. And the types of attributes we use in experimental part are effortless attributes, easily calculated without advanced medical knowledge. Advanced attributes require specialized knowledge or equipment. Non-cyclopedic attributes do not require cyclopedic refraction, and cyclopedic attributes. And actually, the decision value we create based on 3-year spherical equivalent, because the data we have obtained are from two measurements, basic measurements and measurement after 3 years. And to do some binary classification, we have to use some cut points. In particularly, we use the following cut points. M01 means that we divide decision 1 and 0 using the cut point minus 0.5 and so on. Use also minus 4 and minus 1. And to see the balance distribution of different classes, we have made this plot, and actually on the x-axis you have the spherical equivalent after 3 years, and here you have the number of objects from the particular class. So using this cut, for instance, using the cut point M01, you have the really little number of objects in class 1, and a huge number of objects in class 0, yes? And a little bit better situation is for M01 and 05, where class 1 is also rather small, but the balance is a little bit better. The reason to use such cut points was to use some difficult situation when we have the huge imbalance. Actually, we managed with this problem to use something like Smoot and Tomek, techniques for oversampling and undersampling, and we managed this problem to obtain quite nice results. In the future works, we plan to do from the whole classification of the whole spectrum of these cut points. Actually, the smaller resolving values are here. That looks a bit better. Okay, and let me tell you something about the model evaluation methodology. I told you about the Monte Carlo approach, but let me emphasize when the sensitivity, specificity, and precision are important. If we focus on sensitivity to have the high value, actually, it's for the actual myopia risk group. We want to identify as many people as possible and to have the high specificity for people outside the true myopia risk group. We want to warn people as little as possible. It's our main reason. And the precision, the high value of precision means that for people positively classified by the model, we want to have as little as possible for people outside the true myopia risk group. And actually, we focus on high sensitivity and acceptable precision. And use some additional parameter to weight these parameters. Yes, as you can see, the most important for us here is actually sensitivity with the biggest weight. Precision is also here. And actually, the classification model we use in our experimental part, we use logistic regression, k-nearest neighbor methodology, support vector machine, decision tree, random forest, boosting, neural networks, and many more, but that's one of the most important. In regression models, we use the following models, and we use some combined classifiers. We use some pairs of models or more in the same time. And let me show you some example results where we focus on, for instance, Q05 is just the percentile in which we focus on the among 5% of the worst results among methods. We made some ranking of techniques. And actually, for the cut points M01, M02, and M05, we have obtained the following results. The best method for these techniques are as follows: random forest, support vector machine, and combination of logistic regression and random forest. And we focus on the following quartiles of these parameters, and this is just classification for cyclopedic attributes. And let me show you some visualization of these results. It's as follows. As we expected for Q50, we have better results here, we better the point for these particular parameters. And let me show you the results for non-cyclopedic attributes. Actually, in that case, for these cut points, we obtain the best results for combination of logistic regression around the forest for M01, support vector machine for M02, and random forest and for M05. And here you have the visualization of this result, similar as previous one. And actually, I would like to show the results for regression. In regression models, we just trying to estimate the spherical equivalence after 3 years using the conditional attributes. And here you have the results. The best method for cyclopedic attributes are gradient boosting and random forest. And as you can see, we computed for the following percentiles, which are reasonable in that case, and for some specific parameters, mean square error, root mean square error, and so on. And here we have the visualization. And actually, for non-cyclopedic attributes, gradient boosting and artificial neural network wins. Results are as follows. You have the visualization. And let me tell you a few words concluding this presentation. Actually, our Monte Carlo approach is rather simple, reasonable to evaluate the classification, spheres, and regression models. And in our case, we observe that a promising model can be developed on our webpage. It is just lasso regression, logistic regression with lasso. And we have obtained some promising results from non-cyclopedic option. And actually, in showing performance, it's actually important not to focus on the top few results, best results, but to look cross-sectionally at the performance. And we have done it. And in future plans, we would like to obtain some additional data to feed our models and to compare the effectiveness on some another perspective, and to expand non-invasive diagnostic methods, and actually to share the children's myopia risk calculator widely using our webpage. And I would like to stop my talk, waiting for questions. Thank you very much.
Hello, everybody, again. It's time for a discussion. We have two our Polish speakers with us, Mr. Wasilewski and Professor Artemiev. Unfortunately, our Chinese colleague is missing. So we have a Polish, discussion club now. Hopefully, we will get some questions from the audience. We wait for these questions on the chat. So just to continue what was mentioned at the end by Professor Artemiev, yes, we invite everybody who has a data set on, let's say, longitudinal data on children refractive error. So this is very important for us. So this is also a sort of the open invitation to anybody who would like to join our scientific team, consortium with the data. Of course, more data is better. Yeah, and I have a question to Mr. Wasilewski, who just disappeared for a moment, I see. Okay, hello again. Yeah, so what was your data set? Could you repeat it? Because I probably missed that.
We've got data set from Gdańsk University of Technology, from Professor Rumiński. It consists of thousands of OCT images. I think it was around 6,000, but it was 2 years ago, so I would need to confirm it.
Is this data set, well, let's say, prepared by him? I mean, it's quite unusual that the Polytechnic University has access to such a big data set, like several thousands of patients. How they get this data set?
To my knowledge, they collaborate with GUMET, with Gdańsk Medical University, and that's a collaboration, and they got data from them.
So this data finally originated from the medical university?
Yes.
Okay, but still, it's a big data set. Is it, well, as I understand, this is not publicly available data set? You just
as far as I remember, no. As far as I remember,
you have the access based on some sort of agreement, yeah? And
exactly.
Yeah, and what was the proportion in this data set of the labeled to unlabeled images?
Around half was labeled, and the issue that that arose was that to annotate another half, we would need lots of money.
So yeah, I understand. I remember this point. Yeah, of course, from your
talk. So around half of the data set was
So
labeled.
could you repeat what was the number of the images? How big was data set? Because so I don't. It was 1,000 or few thousand. Remember?
Few thousand, but I will confirm it. But a few thousand.
Few thousand, but more 2 or 3 or 7, 8? No, you don't remember. 5,000. What? It's a lot of. You mean images or patients? Because
images. No. Images.
Images.
However, I might be wrong because there were like many data sets, especially many medical data sets. So I will confirm. I will confirm this OCT data set size. But as far as I remember, it was a couple of thousands.
Well, so how many patients?
I suppose one image per one patient.
Well, okay, so finally it would be easy. If it's one image for one patient, it would be 5,000 patients.
Yeah.
Or maybe I think eyes, I would say, maybe depending on. I mean, sometimes we do both eyes depending on the. As a matter of fact, usually we do both eyes. So it could be 5,000 images for 2,500 patients.
Yes.
However, very often we do more images for patients. Both on OCT, we usually have a few scans per eye, and also with the fundus pictures, we have a few fundus pictures per eye. Okay, I mean, just to understand that.
Yeah.
And well, what was the labeling process? What is the accuracy of labeling?
Residents.
That the label was accurate.
We didn't know the residents. We also tried to develop the cross validation between the graders.
Yeah.
However, we didn't finish it, and the project has finished. But we attempt
Because
to.
when the labeling, when the grading is poor, the whole study will be poor.
Yes, but labeling one picture is pricey, and labeling one picture 3 times, for example, if we want to cross validate graders, is 3 times more expensive. So that was the limitation.
Yeah, I know, but the research is expensive. I mean, we cannot do some, shortcuts when we do research. I mean, finally, if you have no money, I mean, you cannot start doing research. Yeah, so I think it's not a good answer that for poor labeling. I'm not sure if it was poor, but the question is how accurate, how good it was. Yeah. So then, without a good labeling, I think there is no really. Good way to start this study because
Totally agree. However, as I observe, the AI community goes more to self-supervised learning. We need much less data, labeled data, than we needed in case of supervised learning. And we were conducting this study 3 years ago, and that was the supervised learning era, so we needed labels. Right now we pre-train the neural network to reconstruct the OCT image and then just fine-tune to one particular task, and in that approach we need much less data. But I totally agree, and I feel a little silly that I haven't refreshed this knowledge. How many what was the exact size of the data set? From my knowledge, it was around a couple of thousands, but I will confirm it, and I will, I will. Right.
Thank you. I know well how difficult it is to collect a data set of let's say that is already graded by expert, because then, well, the first point that you need to have at least a few graders. Well, usually it would be the best is to have three graders, because when you have two and you have a disagreement between them, then you have a problem. So then when you have three, well, it is much better for the let's say reliability of the data set. But then another problem is that they need to have some experience. Otherwise, if you take just very young doctors, again, you have a very poor quality of the grading. Yeah, so you need
Yes.
expert graders, human graders. So it's expensive, I agree. But then you can build a nice data set, and then this data set can be really used for future studies.
Yes, exactly. Completely agree. Just to add one additional thing, we were also attacking this problem of unexperienced graders because usually these are young doctors, as your professor mentioned. So we identified one oracle, so the professor, the Gumet, who was certain, and his grades were treated as ground truth and 100% certain. And then there were few graders which graded and the images, and if there was a disagreement, the oracle decided, and based on that we calculated the accuracy on of the grader, and then we weighted if there was a disagreement, we weighted the decision by by the accuracy of the grader, and this accuracy was obtained by the validation with the oracle. So that was the labeling process of the data set. However, it turned out that it was very expensive, so that's why the selecting of the images that we want to grade was the crucial problem. So that was the motivation.
I can tell you, we started this issue. I can share with some of my experience, and we publish a paper on that. So this is free available. You can find it. I think it was published in Journal of Clinical Medicine, I think like 2 years ago, about the grading. And we asked three experienced retina experts in Poland to grade the same data set, of course. And the agreement rate between these three experienced retina experts were less than 70%.
Less than 70%. Okay.
Okay, and even in I think 21 patients, there was no agreement between two. So three of them provided different opinion. So we must have had a meeting. I organized this meeting online, by the way, because they are located in different parts of Poland. Meeting to discuss these cases. And if I remember well, because of course it was already 2 years ago, we agreed on majority, maybe again 70% of these cases, but still within the 6 or something cases, they kept with the initial opinion. So after even discussion, they say that we will not change our opinion. So it is complicated. I can tell you why also it is complicated in such a countries like Poland, because in Poland, well, we do not have a tradition and also expertise in grading. I mean, we as a doctors, we rarely grade images. So in some countries like in UK, in US, in Singapore, for example, in these countries where they do grading on a, I would say, standard fashion. I mean, for any reason. I mean, in UK and in Singapore, they have national screening programs. And the people who do grading, they are not doctors, they're graders. They are, let's say, people I don't know what is their background education, probably not so important, but they are trained graders and they are certified graders. So they must provide really a qualification to grade, to do only grading, and they are very good in grading. So when often use even the experienced retina doctor who never did grading for such a work, his performance might be relatively low. And this is our experience from Poland. I would say the study. If you are interested, you can look at it. And one of the conclusions was that not that these doctors were poor doctors. No, they were good doctors, but the experience in grading was not very high. Okay, I don't see any more questions. So if you don't have any other comments on issues to be raised, then we can, I think, have a break. We still have some time before the next session. Thank you so much for being with us today.
Thank you very much.
Hello, I'm Olivier Ménage from Mona Health. I will present you the EU regulation in AI. We will review AI in ophthalmology. We will review the regulatory landscape with the three main regulatory frameworks, which are the CE marking for AI devices, the AI Act, the GDPR, the General Data Protection Regulation, the implications for practitioners and developers, and future outlook. Introduction to AI in ophthalmology. Artificial intelligence involves the use of algorithms to perform tasks that typically require human intelligence. The current application of AI in ophthalmology are image analysis for diabetic retinopathy screening, glaucoma detection, EMD, predictive analytics for patient outcomes or surgical outcomes, or automated grading. The benefits of AI in ophthalmology are enhanced accuracy, increased efficiency, early detection, cost effectiveness of care. The challenges and considerations are data quality and bias, regulatory compliance, integration into clinical practice, and legal issues. Regulatory landscape in Europe. The regulatory framework in Europe is designed to ensure the safety, efficacy, and performance of medical devices, including those that incorporate AI. This framework is crucial for protecting patient health, fostering trust in medical innovations, and ensuring that AI technologies are used responsibly and effectively within the healthcare sector. The key regulatory bodies. National competent authorities. Each EU member state has its own national competent authority responsible for implementing and enforcing medical device regulations at the national level. Examples of NCAs include in Germany, the Federal Institute for Drugs and Medical Devices, in France, the National Agency for the Safety of Medicines and Health Products, in the UK, Medicines and Healthcare Products Regulatory Agency, or MHRA. National competent authority are tasked with a range of responsibilities, including the evaluation of medical devices from market approval, post-market surveillance, to monitor the safety and performance of devices in use, and the enforcement of regulatory compliance. Medical Device Regulation, or MDR, and AI. The MDR, which replaced the previous Medical Device Directive, MDD, came into full effect in May 2021. This regulation provides a comprehensive framework for the marketing, distribution, and use of medical devices within the EU, including, of course, AI devices. The key provisions relevant to AI are risk classification. Devices are classified based on their risk to patient health. Clinical evaluation. Manufacturers must provide robust clinical evidence demonstrating the safety and performance of their AI devices. Post-market surveillance. Continuous monitoring of devices is required to detect and mitigate any risk that arise during their use. Manufacturers must collect and analyze data on device performance and report any adverse events. Transparency and traceability. The MDR mandates detailed labeling, unique device identification, known as UDI, and registration into the European database on medical device, called EUDAMED, to ensure transparency and traceability. CE marking for AI devices. CE marking is a certification mark that indicates a product's conformity with the European Union health, safety, and environmental protection standards. It's mandatory for products sold within the European Economic Area. This is a critical step for manufacturers to legally market their product in the EEA. The CE marking process. The first step is determining the device's risk class, which dictates the level of regulatory scrutiny. Devices are classified into 4 classes, Class 1, 2A, 2B, and 3, based on risk. The classification depends on factors such as the device's duration of use, invasiveness, and potential impact on patients' health. For lower risk devices, Class 1, manufacturers can perform a self-assessment to demonstrate conformity with regulatory requirements. For higher risk devices, 2A, 2B, 3, manufacturers must involve a notified body, an independent organization designated by an EU member state to conduct a conformity assessment. This involves a detailed review of the device's design, manufacturing process, and performance to ensure it meets regulatory standards. Manufacturers must provide comprehensive technical documentation, which includes a detailed description of the device, including its intended use, components, and functionality, a risk management plan that identifies potential risk associated with the devices and outline measures to mitigate them, clinical evaluation evidence demonstrating the clinical safety and performance of the device based on clinical data and relevant literature, a post-market surveillance plan for monitoring the device's performance and safety after it has been marketed, including procedures for reporting and addressing adverse events. The manufacturer declares that the device complies with all relevant EU regulations and standards, and then the manufacturer affixes the CE mark. There are post-market obligations. After obtaining the CE mark, manufacturers must continuously monitor the performance and safety of their AI devices. This includes collecting data and analyzing data on adverse events and feedback from users. Any incidents or adverse events involving the AI device must be reported to the relevant competent authority. The challenges in the CE marking process for AI device is the complexity of AI algorithms and the dynamic nature of AI systems. AI devices often involve complex algorithms and large datasets, making it difficult to validate and demonstrate compliance with regulatory standards. Second regulatory framework is the AI Act. The AI Act is a landmark piece of legislation designed to create a harmonized regulatory framework for artificial intelligence across Europe. Its primary goal is to ensure that AI systems used within the EU are safe, transparent, ethical, and respect fundamental rights. The AI Act aims to regulate AI technologies based on their risk levels, ensuring that they are used responsibly and ethically. It seeks to protect the safety and fundamental rights of individuals and society while promoting AI innovation and competitiveness in Europe. So key provisions about the AI Act are first, risk-based classification. The AI Act categorizes AI systems based on their risk to public safety and fundamental rights. First, there is unacceptable risk. AI systems that pose a clear threat to safety, livelihood, and rights are prohibited. Examples include systems that manipulate human behavior in ways that cause physical or psychological harm, or those used for social scoring by government. Then you have high-risk devices. So all healthcare AI devices are classified as high risk. These systems have significant implications for individual safety and rights, necessitating strict regulatory requirements. Examples include AI use in critical infrastructures, healthcare, law enforcement, and employment decisions. High-risk AI systems must comply with the stringent requirements to ensure their safety and reliability. And then you have limited risk, which are like chatbot, and minimal risk, which are like video games. High-risk AI systems must meet several stringent requirements to ensure their safety and reliability. First, a risk management plan. Implement a comprehensive risk management system to identify, assess, and mitigate risks associated with the AI system throughout its life cycle. Ensure high-quality datasets for training, validating, and testing AI systems. This includes measures to avoid bias, ensure accuracy, and maintain the representativeness of data. Maintain detailed technical documentation to provide traceability and accountability for the AI systems development and deployment. This documentation should include information on the design, algorithms, data sources, and testing procedures. Provide clear and understandable information to users about the AI system's capability, limitations, and intended use. This helps users make informed decisions and understand the AI system's role in their interactions. Ensure appropriate human oversight mechanisms are in place to monitor the AI system's decision and intervene when necessary. This helps prevent errors and ensure that critical decisions can be overridden by human judgment. Governance and enforcement of the AI Act. European Artificial Intelligence Board will oversee the implementation of the AI Act, providing coordination, guidance, and monitoring. It ensures consistent application of the AI Act across all EU member states. Each EU member state will designate a national authorities, like the National Competent Authority for AI in healthcare, responsible for implementing and enforcing the AI Act at the national level. These authorities will conduct inspections, audit, and enforce compliance with the AI Act. Penalties. The AI Act includes significant penalties for non-compliance, especially for high-risk AI systems. Penalties can include substantial fines up to 35 million or 7% of the company's total worldwide annual turnover, emphasizing the importance of adherence to regulatory standards. If we look at the date, so on March 13th, the AI Act was approved by the European Parliament. On May 21st, the Council of the European Union formally adopted the AI Act, and it will be published to the official journal of the European Union in June-July. The third framework for regulatory for healthcare and AI is a General Data Protection Regulation, as known as GDPR. So the GDPR is a fundamental piece of legislation designed to protect the privacy and personal data of individuals within the European Union. The GDPR aims to give EU citizens more control over their personal data and to unify data protection laws across Europe. It imposes strict rules on how personal data can be collected, stored, processed, and shared, with significant penalties for non-compliance. AI systems in ophthalmology often processes large volume of personal data, including medical images and patient records. Compliance with GDPR is essential to ensure that this data is handled responsibly and ethically, protecting patient privacy and fostering trust in AI technologies. There are key provisions in terms of GDPR. AI systems should use a minimum amount of personal data necessary for their purposes. This principle requires that only data that is directly relevant and necessary for the task and at hand should be collected and processed. GDPR grants several rights to individuals, known as data subjects. This includes the right to access their data, the right to correct inaccuracies, the right to erasure, also known as the right to be forgotten, and the right to restrict or object to certain processing activities. Patients can exercise these rights to control how their personal data are used by AI systems. Organizations must provide clear and transparent information to data subjects about how their personal data is being used. This includes informing patients about the purposes of data processing, the legal basis for processing, data retention periods, and the rights under GDPR. Robust security measures must be implemented to protect personal data from unauthorized access, breaches, and other security risks. This includes encryption, access control, and regular security assessments to ensure that patient data remains secure throughout its life cycle. Of course, there are interactions between GDPR and AI Act. GDPR and the AI Act work together to ensure that AI systems are both safe and ethical. While the AI Act focuses on the safety, transparency, and accountability of AI technologies, GDPR ensures that the personal data used by these systems is protected. Compliance with both regulations is crucial for AI developers and healthcare providers. The integration of AI technologies in ophthalmology presents significant opportunities for improving patient care, diagnostic accuracy, and treatment outcomes. However, practitioners must navigate a complex regulatory landscape and adhere to various compliance requirements to ensure the safe and effective use of AI tools. Here are the key implications for ophthalmologists. Ophthalmologists must have a thorough understanding of the capabilities and limitations of the AI systems they use. This includes knowing what the AI system can do, such as detecting diabetic retinopathy, glaucoma, or AMD, understanding its diagnostic algorithms and decision-making process. Being familiar with the system's accuracy, sensitivity, specificity, and any known limitations or potential sources of error, recognizing that while AI can enhance diagnostic capabilities, it's not infallible and should be used as a complement to and not a replacement for clinical judgment. Understanding the conditions under which the AI system performs best and recognizing scenarios where its performance may be less reliable. This includes consideration factors like image quality, patient demographics, and the presence of other eye conditions that might affect the AI's accuracy. AI tools used in ophthalmology must comply with various regulatory frameworks, including CE marking, the AI Act, and GDPR. Practitioners must ensure that the AI system in use have obtained the necessary CE marking, indicating that they meet EU health, safety, and environmental standards. They comply with GDPR by implementing robust data protection measures and ensuring patients' right to access, correct, and delete their data are respected. To maximize the benefit of AI technologies, ophthalmologists should engage in continuous education and training. This includes workshops and seminars, online courses, collaborative learning. Effective communication with patients about the use of AI in their care is crucial. Ophthalmologists should clearly explain to patients how AI systems are used in their diagnosis and treatment, including the benefits and limitations. This helps build trust and ensures patients understand the value of AI technology in their care. Be prepared to address any concerns or questions patients may have about AI technologies, ensuring they feel comfortable and informed. Transparency about the AI system's capability, data usage, and potential risk is essential. The integration of AI technology in ophthalmology brings significant advancement, but also requires practitioners to adapt to new responsibility and practices. Future outlook. The future of AI in ophthalmology holds immense promises, driven by continuous advancement in technology and evolving regulatory frameworks. Understanding these future trends and preparing for them is crucial for both practitioners and developers. Here are the key aspects of the future outlook of AI in ophthalmology. Regulatory frameworks such as the AI Act and GDPR will continue to evolve to address emerging challenges and advancement of AI technology. Regulators will likely introduce updates and refinement to ensure this framework remain relevant and effective. There will be ongoing efforts to harmonize AI regulations globally, making it easier for AI developers to comply with standards across different regions. This global harmonization will facilitate the international deployment of AI technologies. There will be technological innovations. The development of more sophisticated and accurate AI algorithms will enhance diagnostic capabilities in ophthalmology. These advancements will enable earlier detection of eye disease and more precise treatment plans. AI will increasingly integrate with other emerging technologies such as augmented reality, virtual reality, and wearable devices. This integration will provide comprehensive solutions for eye care, enhancing both diagnostic and therapeutical capabilities. AI will play a pivotal role in the shift towards personalized medicine. By analyzing large datasets, AI systems can identify patterns and correlations that lead to more individualized plans, improving patient outcome. As AI technology becomes more prevalent, there will be a stronger emphasis on ethical AI development, ensuring fairness, transparency, and accountability in AI systems will be paramount. Maintaining patient safety will remain a top priority. Continuous monitoring, rigorous testing, and compliance with regulatory standards will be essential to ensure AI systems are safe and effective. Conclusion. As we conclude our exploration of AI regulations in ophthalmology in Europe, it's essential to recap the critical point and emphasize the importance of staying informed and compliant in this rapidly evolving field. In summary, understanding and complying with AI regulations in ophthalmology is essential for ensuring patient safety and fostering innovation. CE marking certifies the safety and efficacy of AI devices, while the AI Act provides a comprehensive framework for ethical AI deployment, categorizing systems based on risk level. GDPR ensures robust data protection, safeguarding patient privacy. Practitioners must stay informed, engage in continuous education, and communicate effectively with patients, while developers must focus on compliance, transparency, and ethical AI design. By navigating these regulatory landscapes, we can leverage AI to enhance patients' care, drive innovation, and build trust in these transformative technologies. Thank you for your attention. I welcome any question you may have.
Hello everyone, my name is Alvin Liu. I'm a retina specialist at the Wilmer Eye Institute, Johns Hopkins Medicine. It is my pleasure to speak here today, and thank you for the kind invitation. I do not have any financial disclosures. Today for my talk, I have three main objectives. First, I would like to discuss the major stakeholders, agencies, players, and considerations related to medical AI regulations in the United States. Second, I would like to use autonomous AI for diabetic eye disease testing as a use case to demonstrate my key points. Third, I would like to discuss the major uncertainties and unknowns in this area. The first and perhaps most important player in the landscape of medical AI in the US is the US Food and Drug Administration. As I mentioned previously, medical AI models in the US are typically regulated as medical devices. When it comes to medical devices under the purview of the FDA, there are four major pathways: Class 1, Class 2, Class 3, and alternative. So Class 1 devices are typically low-risk devices that do not require FDA approval. Class 2 devices have moderate risk that require clearance by the FDA, and the company must complete a 510(k), also known as pre-market notification. Class 3 devices are classified as high risk. FDA approval is required, and the company must complete the pre-market approval process. Last but not least, there's also an alternative pathway, also called a de novo process for low or moderate risk devices without a predicate. In May 2024, the US FDA released a list called Artificial Intelligence and Machine Learning Enabled Medical Devices that summarizes the list of AI devices approved to date. Of these 882 devices, 151 of them were approved between August 1st, 2023 and March 31st, 2024, indicating a sustained rapid pace of approval. Within these devices, radiology-related uses dominated, accounted for about 76% of these devices. Other leading therapeutic areas include cardiovascular use cases, accounting for about 10% of these devices, neurology devices, accounting for about 3.6% of these devices, and to date, ophthalmic devices coming from 6 companies account for about 1% of the total number of devices, and the total number of approved ophthalmic devices are 9 to date. A lot of these AI devices were approved through the de novo pathway. As I mentioned previously, when it comes to medical devices, there are 4 major pathways through the FDA. The de novo regulatory pathway is meant for low to moderate risk devices that are novel and for which there's no prior legally marketed devices. A lot of these devices, including ophthalmic devices, were also designated as breakthrough devices. In order to be eligible for the breakthrough device program, the device has to meet one of the following criteria. For example, it must represent a breakthrough technology, or there must be no approved or cleared alternatives, or the device must offer significant advantages over existing approved or cleared alternatives, or the availability of the device is in the best interest of patients. And the breakthrough device program is meant to expedite the review process. The next key concept when it comes to medical AI devices in the US is something called the Current Procedural Terminology, CPT code. It is designated by the US Department of Health and Human Services under the Health Insurance Portability and Accountability Act as a national coding set for physician and other healthcare professional services and procedures. CPT codes are set by a panel called the CPT Editorial Panel, which is an independent group of expert volunteers representing various sectors of the US healthcare industry. And this CPT Editorial Panel is in turn supported by CPT advisors, which are groups of physicians nominated by the National Medical Specialty Societies. The CPT Editorial Panel was created more than 50 years ago, and this is a process convened by the American Medical Association that ensures clinically valid codes are issued, updated, and maintained on a regular basis. The CPT Editorial Panel meets 3 times a year to review the applications for either new codes or revisions to existing codes. In the previous slide, I talked about the importance of the CPT code. CPT codes are important because that's how healthcare is paid for in the US, which means if AI technology in the US, and specifically ophthalmic AI technologies, are to be sustained, we need to establish CPT codes to pay for these devices. And then the next question becomes, who is going to pay for these medical devices? And the answer is insurance payers. So as a background information, the healthcare sector in the US is about $4.5 trillion a year, and about 92% of Americans have medical insurance coverage. That means the vast majority of healthcare payments, including payments for medical AI devices, is conducted through medical insurance payers. In the US, there are 2 major types of medical insurance, government-run insurance programs and privately run insurance programs. Government insurance programs are devised and run by an entity called CMS, Centers for Medicare and Medicaid Services, and the CMS is a federal agency within the United States Department of Health and Human Services. Medicare is the single largest payer for healthcare services in the United States, and it covers about 19% of Americans. In addition to Medicare, the CMS also administers Medicaid, which is an insurance program for low-income individuals, and Children's Health Insurance Program. When it comes to private medical insurance, the 5 biggest private payers are United, Elevance, Centene, Aetna, and Cigna. And the alignment of payers is important because ultimately, just because we have CPT codes set up for medical AI devices doesn't mean the payers are willing or able to pay for it. Specifically, it is critical to get CMS coverage for a particular ophthalmic AI device to ensure national coverage. And in the US, typically commercial or private insurance payers will follow the footsteps of the CMS. This is a recent publication in the journal NEJM AI, and this particular paper looked at the clinical adoption and payment of medical AI devices across the US based on insurance claims. This is an important figure from the same paper that demonstrated the adoption of clinical AI based on medical specialty. As you can see here, the second most commonly used CPT code is actually in ophthalmology, specifically in the use of autonomous AI for diabetic retinopathy testing. And this is both surprising and encouraging because if you remember from the earlier part of my talk, out of the 882 medical AI devices approved to date, ophthalmology only accounts for about 1% of these devices. However, when we look at real-world implementation of medical AI technologies, ironically, ophthalmology is actually number 2 when it comes to the prevalence of adoption and implementation. And as you can see from the graph here, the rate of adoption in ophthalmology is improving and increasing rapidly. It is fair to say that ophthalmic AI devices, specifically devices meant for autonomous AI detection of diabetic eye disease, is leading the charge in both research and real-world implementation in the US. And I think this can be attributed to several different reasons. In the following part of the talk, I would like to highlight several key reasons for the success of ophthalmic AI technologies in the US. The first key factor for success in the real world is to have good science behind the products. Currently in the US, there are 3 companies with FDA-cleared products for the purpose of autonomous AI detection of diabetic eye disease. And these 3 companies are Digital Diagnostics, iNook, and AI. All 3 companies and their products underwent vigorous scientific validation in the form of clinical trials. The second critical factor for success is the establishment of relevant CPT codes. As I mentioned previously, having a CPT code is very important because that's how healthcare is paid for in the US. In the case of autonomous AI for diabetic eye disease testing, a new specific CPT code was established, and this CPT code is 92229. The third critical factor for success is to engage with and negotiate with payers early in the process to ensure that the AI-specific CPT code will be reimbursed for. So in the case of autonomous AI for diabetic eye disease testing, this was done in parallel early on, even when the clinical trial was being set up. So for example, for this particular ophthalmic AI technology, reimbursement has been established for both government and commercial insurance payers. This in turn also ensured national coverage. The fourth critical factor for success is to build alliances with professional societies. In the case of autonomous AI for diabetic eye disease testing, there are 2 key allies. First, the American Diabetes Association updated their recommendations that an FDA-approved AI system capable of detecting more than mild diabetic retinopathy could be an alternative to traditional screening approaches. Second, the National Committee for Quality Assurance specified that an eye exam evaluated by AI interpretation would comply with HEDIS requirement. HEDIS reporting is a requirement of health plans for use in health plan accreditation and star ratings, which means that HEDIS measures have direct reimbursement implication. Despite the generally positive environments for medical AI devices in the US and the acceleration in the adoption of ophthalmic AI devices, major uncertainties remain in this area, and I can think of 5 of them. First, the FDA is familiar with how post-marketing monitoring should be done for therapeutic drugs. However, currently, there's no consensus on how post-marketing monitoring should be done for medical AI devices. Second, once an AI model is approved by the FDA, it is then locked, meaning no further updates can be done. However, this regulation does not allow for future updates of the models to account for data drift. Third, currently, an AI model can only be approved by the FDA once both safety and efficacy are shown. However, in reality, this could be quite burdensome and may stifle innovation. For the future, one could consider approving these AI models once they've been shown to be safe, and their efficacies can be evaluated after they've been approved. Fourth is something called the HTI-1 final rule. So this rule implements provisions of the 21st Century Cures Act. It establishes first of its kind transparency requirements for AI and other predictive algorithms that are part of certified IT, such as electronic health record. The basic idea is that there will be a baseline set of information about algorithms that will be made available to users, such as doctors, in the electronic health records. However, how exactly these information will be presented and the related enforcement mechanism remain unknown. Last but not least, the rise of large language models. If we look at all the medical AI devices approved to date, their indications and labeling are very specific, meaning these medical AI devices were approved for very specific purposes. However, with the rise of multimodal large language models that are capable of accepting and generating multimodal information, it remains completely unclear how these large language model products will be regulated in the future. Thank you so much for your attention, and that's all I have.
Hello everyone, I'm Dr. Sheila John, Head of Teleophthalmology, Shankar Nethralaya, India. My topic today is Indian regulations on artificial intelligence. I would like to thank the organizers for giving me this opportunity. Artificial intelligence in healthcare has revolutionized diagnosis, investigations, treatment, and patient care in ophthalmology. It enhances accuracy and efficiency in medical procedures, focuses on teleophthalmology, remote diagnosis and management of various eye conditions is feasible. It is critical for addressing diabetic retinopathy, a leading cause of blindness in diabetic patients. Diabetic retinopathy and its impact. More than 70 million diabetic patients in India. Prevalence of diabetic retinopathy is 18 to 20% in diabetic population. Screening for BR to identify 5 to 6% of sight-threatening diabetic retinopathy. It is especially useful in remote areas where there is lack of human graders to support the screening of diabetic retinopathy. We need preventive eye care through early detection of DR to prevent blindness. The role of AI in teleophthalmology. AI-powered solutions, especially images and artificial intelligence, play a pivotal role in eye assessment. And artificial intelligence is able to diagnose many image. Artificial intelligence works on automated image analysis for early detection of various eye diseases. And AI algorithms identifies retinal and all ocular diseases. The benefits are increased accuracy and efficiency, scalability to reach remote areas. The AI tools for diabetic retinopathy are AI-based screening tools like retinal imaging devices integrated with artificial intelligence like fundus cameras, OCT machines, cloud-based AI platforms for real-time analysis. Examples in India is deployment in hospitals and mobile units, collaboration with healthcare providers, and mainly it is screening of diabetic retinopathy which is carried out in various parts of India. Automated diabetic telescreening in India, especially in rural areas. Automated AI screening system further reduce the workload for human graders, mainly ophthalmologists, and you can take minimally skilled technicians to participate in the eye care delivery process. Additionally, the process is considerably cost effective in rural areas and in less developed countries compared to manual grading. Government initiatives, the support for artificial intelligence in healthcare, the National AI Strategy with the NITI-AYOG, AI for All campaign promoting healthcare innovations. The AI for All, it is taken up in India as a mission to catalyze the AI innovation ecosystem to ensure the global competitiveness of India's AI startups and researchers. And we have many scientific programs initiating targeting eye care, and main focus is on diabetic retinopathy. Regulatory framework for AI in healthcare. Current regulations, the IT Act 2000, general regulations impacting artificial intelligence. Then in 2017, you had the medical device rule, regulations for AI-powered medical devices. The regulatory bodies are Ministry of Electronics and Information Technology, MeitY, Central Drug Standard Control Organization, CDSCO. Very important is the Draft Personal Data Protection Bill. The data protection legislation ensures data privacy and security, the pre-provisions impacting artificial intelligence in healthcare. Implications for ophthalmology is handling of patient data and the compliance requirements of the data protection legislation bill. Ethical consideration in AI include addressing bias in algorithms to ensure for equitable access to AI-driven healthcare. We also require transparency and accountability, need for explainable AI models, accountability for all AI decisions and outcomes, as it is very important in healthcare when it brings in the diagnosis of various eye diseases. Challenges in AI implementation. Technical challenges are in relation to data quality and standardization issues, infrastructure limitations in rural areas, the regulatory challenges, ambiguities in existing regulations, and the need for AI-specific guidelines to be formulated by the government. AI in public health initiatives. Government programs are there which integration of AI in national health programs, especially like National Program for Screening of Diabetic Retinopathy, AI-driven initiatives for diabetic retinopathy screenings, case studies, successful implementation examples in the various states. Now, if you take case studies, the Google study was one of the landmark studies in artificial intelligence which was conducted in India. It was a prospective validated performance of automated artificial intelligence DR system in India. The study conducted on 3,049 diabetic patients by Shankar Nethralaya and Aravind Eye Hospital. Automated diabetic retinopathy grading system compared with manual grading by one trained grader and one retina specialist from each site. The automated diabetic retinopathy systems performance for moderate and severe diabetic retinopathy were equal to extended manual grading with a sensitivity of 88% and specificity of 95%, which is a very good. Collaboration with private sector, public-private partnership. Collaboration to develop and deploy AI solutions and the role of technical companies and startups are very important to employ and deploy AI throughout India. The impact is accelerated innovation with broader reach, enhanced healthcare delivery through artificial intelligence. International collaboration, global partnerships, collaboration with international AI research bodies to increase the use of artificial intelligence in the landscape of India and participation and collaboration in global health initiatives. These collaborations help in knowledge exchange and resource sharing, enhance research development in diagnosis of various diseases. Future Prospects of AI in ophthalmology. The future of AI in ophthalmology looks promising with emerging trends such as advances in artificial intelligence algorithms for eye care, integration with wearable devices and teleophthalmology. The potential developments are artificial intelligence driven personalized treatment plans, expansion of AI solutions to other diseases, both in the anterior segment and posterior segment, other than diabetic retinopathy. Skill development and training, building expertise, training healthcare professionals in artificial intelligence tools, incorporating AI education in medical curricula, government and private initiatives, programs to upskill workforce in artificial intelligence and healthcare. Success stories in India. Case study 1, Shankar Nethralaya, Chennai. Use of artificial intelligence in teleophthalmology services, which brings in improved patient outcomes, accessibility for the patient in remote areas. Case study 2 is Aravind Eye Care System, Madurai. Implementation of artificial intelligence for diabetic retinopathy screening. Impact on early treatment, early diagnosis and treatment. Success stories in India, Aditya Jodh Eye Hospital, Bombay, Eye Analysis System in detecting referable diabetic retinopathy on retinal images taken by a health worker with a smartphone, which was based on a portable non-mydriatic retinal imaging system. The application of AI augments the screening for referable diabetic retinopathy in remote areas where services of ophthalmologists are unavailable. Nationwide diabetic retinopathy screening drive to prevent blindness due to diabetic retinopathy. Challenges and barriers. The technical barriers are limited access to high quality data and the infrastructure constraints in rural areas. Now, if you take the regulatory barriers, lack of clear AI-specific regulations by the Indian government, compliance challenges with existing laws. The major recommendation is development of a comprehensive AI regulations and laws by the government for its implementation, policies to ensure data privacy and security, implementation strategies strengthening public-private partnerships, investing in infrastructure and skill development. The evolution of AI regulations in India. Historical content is early adoption of IT laws. At that time, the use of AI was also there. The gradual incorporation of AI-specific consideration was built from the early adoption of IT laws. The key milestones are establishment of an artificial intelligence task force, the introduction of artificial intelligence in policy frameworks, and right now AI for all policy, the National Strategy on Artificial Intelligence, the National Institute for Transforming India, AGOG's, which is NITI. The leading national strategy on artificial intelligence was brought in by NITI AGOG. It has focus on healthcare, agriculture, education, and more. The healthcare specifics brought in by the National Institute for Transforming India was AI for improving healthcare delivery, initiatives targeting teleophthalmology, and the diagnosis of diabetic retinopathy. The regulatory sandbox for artificial intelligence, safe environment for testing AI innovations, collaboration between regulators and innovators is the main purpose of the concept. Applications in healthcare, testing AI solutions for medical diagnosis, ensuring compliance with regulatory standards brought in by the government, HIPAA-like regulation framework in India, introduction to HIPAA, Health Insurance Portability and Accountability Act, HIPAA in the US, protects patient data and privacy. So India's approach is data, draft personal data protection bill as a step towards HIPAA-like standards, provision for healthcare data protection. The key provisions were consent and the right to access personal data, and also to note if there are any breach in data. AI-specific regulations and guidelines, need for AI-specific regulations, addressing the unique challenges posed by AI, ensuring safe and ethical artificial intelligence deployment. Proposed guidelines are framework for AI ethics and governance, guidelines for AI use in healthcare. The role of the regulatory bodies. Key regulatory bodies are Ministry of Electronics and Information Technology, Central Drug Standard Control Organization. Responsibilities is overseeing the artificial intelligence implementation and compliance, ensuring safety and efficiency of AI solutions. International regulatory benchmarks, learning from global examples, comparison with Europe's GDPR and United States HIPAA, adoption of best practices for leading AI regulations, global collaboration, participating in international AI regulatory forums, harmonizing regulations with global standards. HIPAA-like data protection measures, consent and transparency, clear and split patient consent for data usage should be there, transparency in data collection and processing practices, data minimization, collecting only necessary data for specific purposes, reducing the risk of unnecessary data exposure. Data security and privacy measures, encryption and anonymization, encrypting patient data to protect it during storage and transmission, anonymizing data to prevent identification of individuals. Access controls, implementing strict access controls to ensure only authorized personnel can access sensitive data, regularly updating and reviewing access permissions. Data breach response and reporting, breach notification protocols, immediate reporting of data breaches to relevant authorities, notifying affected individuals promptly, incident response plan should be there, establishing a comprehensive incident response plan, regularly testing and updating the response plan. Training and awareness programs should be there with the healthcare provider training, educating healthcare providers on data protection laws and compliance requirements, regular training sessions and updates, patient awareness, informing patients about their data rights and protection measures, providing resources for patients to manage their data privacy. Case studies of HIPAA-like compliance in India, large hospital network, implementation of comprehensive data protection measures, success in preventing data breaches and ensuring patient privacy. If you are a telehealth service provider, adoption of encryption and access controls for teleophthalmology services, positive impact on patient trust and service quality should be there, no matter whether it's a large hospital or a telehealth provider. Challenges in implementing HIPAA-like standards, technical challenges, infrastructure gaps in rural areas, ensuring robust cybersecurity measures. The regulatory challenges are harmonizing various healthcare regulations, training healthcare providers on compliance. Recommendations, strengthening regulations, continuous improvement of data protection and regulations, adoption of global best practices and standards, encouraging innovation, balancing regulation with the need for innovation, supporting the development of AI-driven healthcare solutions. Telemedicine practice guidelines was brought in by the Government of India by 25th March 2020. The legal implications, amendment of the Indian Medical Council Professional Contact and Ethics and Regulation 2002 by the Medical Council of India, enabling registered medical practitioners to provide healthcare using telemedicine. There is no provision for consultations outside the jurisdiction of India. Telemedicine practice guidelines brought in by 25th March 2020 clearly state that technology platforms based on artificial intelligence and machine learning are not allowed to counsel patients or prescribe any medicines to a patient. While new technologies like artificial intelligence, Internet of Things, and advanced data science-based decision support systems could assist and support the registered medical practitioner on patient evaluation, diagnosis, and management. But the final prescription or counseling has to be directly delivered by the registered medical practitioner. Now, the National Artificial Intelligence Strategy, they have put in 7 principles for the responsible governance of AI systems. It should be safe and reliable. It should be inclusive and non-discrimination should be there. Equality should be there. Privacy and security should be built in. It should be transparent as well as accountable. And protection and reinforcement of positive human values. AI for all. AI technologies that enable machines to act with highest levels of intelligence and evaluate the human capabilities of sense and comprehension. There is a national strategy for artificial intelligence. Non-uniform accessibility to healthcare across the country, with physical access continuing to be the major barrier to both preventive and curative health services, and glaring disparity between rural and urban India. Now, to scale up automated detection of diabetic retinopathy using artificial intelligence, what you require is automated retinal image analysis to be practiced in India. They will need to consult government regulatory norms, licenses, and cost. DR algorithm, which is a software, operates as a medical device and follows the international medical device regulations guidelines. There has to be joint planning, implementation, and monitoring of diabetic retinopathy screening by ophthalmologists, physicians, and endocrinologists. We need to have further work on adopting standard guidelines for adopting automated retinal analysis for DR screening programs. The future of artificial intelligence regulation in India. Anticipated regulatory changes are upcoming on specific regulations and amendments. Focus on adaptive and forward-looking regulations. Future of AI regulations in India. Anticipated regulatory changes. Upcoming artificial intelligence specific legislation and amendments. Focus on adaptive and forward-looking regulations. The AI task force, which is being formed by the government. The long-term mission is establishing India as a global leader in artificial intelligence governance, promoting ethical and sustainable AI development. Thank you very much for giving me this opportunity to deliver this lecture in the conference. I once again thank the organizers. Thank you. Any questions?
Good afternoon. Thanks for invitation. I'm Dong Liu, and I am from Zhongshan Ophthalmic Center, Sun Yat-sen University, China. Today, I will give a talk about AI environment in China. At the beginning, I will introduce the National Medical Products Administration, or NMPA. In March 2018, in an effort to establish unified market regulatory authority and considering specialty nature of drug, medical device, and cosmetic supervision, the NMPA was established separately and managed by State Administration for Market Regulation, or SAMR. As a government agency in China, the main responsibilities of NMPA are supervising the safety of drugs, including traditional Chinese medicines and ethno medicines, medical devices, and cosmetics, to regulate the registration of drugs, medical devices, and cosmetics, to undertake standards management for drugs, medical devices, and cosmetics, and so on. NMPA encourages high-quality development of medical devices industry through innovation pathway, priority pathway, real-world data pilot pathway, AI and Campbell support. In 2021, NMPA cooperated with Ministry of Industry and Information Technology, MIIT, to launch the task of AI medical devices innovation, creating a master document registration system, accelerating the approval of new technologies and new products, and helping the high-quality innovation and development of the industry.
According to China's medical device classification rulers effectively since January 1st, 2016, medical devices are divided into Class 1, Class 2, and Class 3, with risk levels rising in sequential order. The risk level is determined based on the device's intended purpose with various other factors, including structural characteristics, the form of use, the states of use, whether the device conducting the body, and so on. The majority of AI medical software products are divided into Class 2 and 3 medical devices in China. Recently, several AI medical product-related regulations were approved by NMPA. For example, in August 5th, 2015, the guidelines for technical review of medical devices software registration was announced. It provides the guidelines for registration and application of medical device software, and the content was proposing registration requirements for software classification, security level, software description documents, software updates, registration and testing units, and registration application materials requirements. Then, more and more regulations were introduced, one after another. A total of 122 AI medical software products have obtained registration certification approved by NMPA up to December 1st, 2023. Among them, there are some AI medical software in ophthalmology. The founder's image-assisted diagnostic software for chronic glaucoma-like optic nerve lesion that developed by Tencent Medical Health Shenzhen company was approved, and Tencent became the first internet technology enterprise in China to be approved for innovative medical devices. The algorithm engine uses multimodal integrated learning stage to give hints on whether there is suspected chronic glaucomatous optic neuropathy, provides hints on suspected chronic glaucomatous optic neuropathy for practicing doctors, and provides auxiliary diagnosis suggestions on whether further medical examination is required. Shanghai Eldo, Beijing Veto, and Beijing Confuzi were also approved for AI medical software in ophthalmology. Next, I will introduce a paradigm of industry university research on AI in ophthalmology in China. That is the Comprehensive AI Retinal Expert Care System, a project initiated by Zhongshan Ophthalmic Center and the Eldo Company. Part of the achievements, Founder's image-assisted diagnostic software for DR were approved by NMPA, which is the first DR medical diagnostic software approved by NMPA. They conducted a national real-world study covering 82% of the Chinese provinces and a total of 51 institutions with different medical levels were involved. This is the study design. More than 260,000 founders' photographs were included in this study. They first trained the DLS and then tested the model in different ways, including internal validation, external test, comparison with single disease neighborhood binary classification models, comparisons with human doctors, and previously unused camera taps. The number of founders' photographs used to model training was more than 200,000. All of the photographs were retrospectively connected from 16 institutions, including 5 tertiary hospitals, 5 community hospitals, and 6 physical examination centers. All of the photographs were classified as normal or labeled with one or more of the following 14 common retinal abnormalities if they have 2 ocular manifestations of systemic diseases, referable DR and hypertensive retinopathy, and 12 vision threatening abnormalities. After labeling, they putted all the photographs with multi-disease labels in a single CNN network and trained the model care. To do so, one of the advantages is all disease information can be shared and help to assist all different diagnoses. Then, improve the model performance at last. Another is to reduce the consumption of computing resources and reduce the dependence on internet connections. More than 21,000 of founders' photographs were included in internal validation, the AUCs of identifying healthy founders and
5 minutes to
14
discussion.
retinal disease was shown in this table. The mean AUC was 0.952 in tertiary hospitals, 0.974 in community hospitals, and 0.940 in physical examination centers. They prospectively collected more than 18,000 photographs from 35 clinical settings all over the country to externally test the model care. From this table, we can see the good performance of care maintained in the external test. They also conducted a comparison between care and human doctors. They found that the performance of care was similar to that of ophthalmologists. However, large variations in sensitivity were observed among the ophthalmologists in different regions and with varying experience. At last, camera tap testing is an important approach to evaluate the model generalization ability. Because most types of camera had been included in the model training and the previous tests, so they tested the model using scanned files of printed founders' photographs from an old film camera, like Canon Tokyo, Japan. This work has been published in the Nest Digital Health, and part of the study obtained the first NMPA-approved AI-empowered retina-based auxiliary diagnostic product. In conclusion, China continues to encourage the innovation and the development of AI medical products, and to strengthen clinical research of AI medical program and enhance collaboration between research and the industry. The rapid development of AI medical products bring more challenges to regulations. And I believe there are more and more AI medical products will be applied in clinic and be approved by NMPA. In the end, I'm willing to talk about Zhongshan Ophthalmic Center, which is the leading AI hospital in China, serving over 1.4 million outpatient visits every year. Zhongshan Ophthalmic Center has been ranked first in ophthalmology by the Best Hospital in China for 14 years in a row. We now serve as the WHO's collaborating Center for Eye Care and Vision and host the headquarters of the Asia Pacific Academy of Ophthalmology, APAO. With its commitment to exceptional patient care, education, cutting-edge research, and global collaborations, Zhongshan Ophthalmic Center remains at the forefront of the ophthalmology in China. In terms of research, Zhongshan Ophthalmic Center hosts China's only state library of ophthalmology, focusing on cutting-edge research in stem cells, neurobiology, and artificial intelligence. We have been ranked number 1 by the Science and Technology Evaluation Matrix for 10 years in a row. Zhongshan Ophthalmic Center serves as a national education base for PhD students and clinical residencies in ophthalmology. Thank you for your attention and welcome to Guangzhou, a vibrant hub of global trade and boundless energy.
Hello, everybody again. Now we can start the discussion. I remind that everybody can put the question on the chat. We have 2 speakers with us, Professor Alvin Liu from Baltimore, US, and Dr. Dong Liu from China. Unfortunately, 2 other speakers are missing. We have no information about them. It's a great pity, but even more, let's say, thanks to those who joined us for the discussion. So, Alvin, well, both talks were very interesting. Well, obviously, we know much more about the American system and American model, but I have 2 questions. The first, well, as we see, there's a big discrepancy, as you mentioned, by the way, between the whole number of AI-based devices, about 900, and about the ophthalmology subfield, about, well, not about, but it was, as I remember, 9 or so, just 1%, not 1%. And so why do you think there is such a small representation? Of course, you explained later that in the reimbursement and the practical application is not as bad. So, oh yes, Dr. Sheila John is with us. Great. So why do you think that there are finally such a small number of ophthalmic devices approved by FDA? Does it mean that it's so difficult to get the FDA approval?
Well, I would say there are several reasons for this. If you look across AI application for ophthalmology, the most obvious use cases nowadays is for the screening of blinding diseases such as diabetic retinopathy or glaucoma. Clearly, this use case is very important for public health purposes. That's why I think we see this technology taking off around the world. The issue with the US is that it's a very fragmented healthcare system, and there's no national public screening program. So it falls upon the private sector, the private companies coming up with these AI models to figure out a business model, meaning the government is not going to subsidize these companies for the purpose of a national screening program. So I think that's why economically it's not easy to do ophthalmology AI in the US, and hence there are relatively few companies. But at the same time, on the flip side, because the economic model is not as easy to figure out, I think for the existing companies, they really have thought really hard and long about how to make this financially viable.
Thank you. But well, I think that the economical environment, well, of course, is different, but it's not, I don't believe it's much easier in Europe. But as you know, at the European Union level, we have over 20 AI-based devices only for diabetic retinopathy that are registered, and the for ophthalmology subfield is much more. So why the question is why these companies they take the registration in the European Union, they do not go to US. This is my question. I mean,
Oh, I see what you mean. I think there are two main reasons for it. And I've talked to companies who currently have CE mark but have not been approved in US. I think overall speaking, the requirements to go through FDA approval is more stringent scientifically. Also, it costs a lot more money. I think these two are the main reasons. So.
Thank you. Yeah, I agree. This is the right point. And the second question you mentioned about the safety and efficacy. Of course, we understand well what efficacy means, but what do you mean by safety? You know, when you mention about the FDA approval, safety versus efficacy.
When I say safety, there are probably two main areas. One is bias, and one is very poor performance in certain subpopulation. So I can imagine a scenario where if you can demonstrate that your ophthalmic AI model or any medical AI device does not show particular bias against a subpopulation, and that it does not perform particularly poor in a subpopulation, then perhaps this, meaning that's what I mean by safety. It does no harm, then perhaps such a model can be approved, even though the overall performance is not spectacular.
Thank you. A bit complicated, but of course I understand what do you mean. Yeah. Well, we still have no questions, but I have a question to Dr. Dong Liu. Well, you know that in the US it is very easy to check the both, I mean, the regulations and also the information about the FDA approved devices. It takes about, well, minute or 5 minutes. Is very easy. So what about China? Is it possible? Does such a register exist, and is it available? I mean, publicly, or this is my first question.
Thank you for your comment. Actually, in China, the regulations are always written by Chinese. So the English language are still writing now. So you should read the Chinese of this regulations.
Do you have such a register? But well, let me ask another way. Do you have such a register? That, well, even Chinese person, I asked a Chinese colleague who lives in Guangzhou, please check how many AI-based medical devices are registered in China in ophthalmology. Is it possible to check it, well, or not? The question.
Actually, in Guangzhou, it is easy to reach the AI ophthalmology devices such as
it was just an example, Guangzhou. It could be Shanghai. I mean, any
Shanghai.
No.
Okay, I see.
I mean, the whole country.
For example,
whole country.
All country. Yeah. In Beijing, in Shanghai, and Guangzhou, the AI ophthalmology devices or system can reach easily. In other provinces like Xinjiang, is also easy to reach this AI system.
And the second question, because you shown the table presenting some AI-based devices in ophthalmology that are obviously registered in China, I just try to calculate. I think that there were 6 or 7 could you give the final number of the all AI-based devices in ophthalmology? Well, for example, Professor Yu gave the a final number based on the FDA register. So is it possible for China also to say that?
In this time, it is hard to say that.
Not possible.
Yeah, it is impossible to read this now.
Why? You don't know how many devices are registered in China?
Yes, it's being a decreasing number year by year. So
well, of course, I mean for let's say the end of December last year. I don't speak about changes. I mean during the time, but okay. Yeah, thank you. I mean, I think, well, in Europe, we have also, unfortunately, the colleague, I mean, the Mr. Mensch, who presented the European part is missing. But in Europe, we have no clear situation for those who know it. We have no such a register. It was started recently, UDAMED, and hopefully it will provide the information as FDA register in the future. But still, we have no access to such a register. We could check every device that is registered. So yeah, but Europe is based on different countries. I mean, we have so many different countries. Well, regarding China, I thought that is a more centralized system and that is easier to get such a knowledge. Well, let's move to India now, because I have a question to Dr. John. Do you have such a register in India? So, for example, you know which AI devices are registered in ophthalmology?
Basically, most of the devices are taken from FDA approval from US. There are no, as far as now, there are no separate equipments which are made in India, but it follows the, whatever that medical devices with AI. We can find out through the biomedical department, which is there in the government. We have something called Indian Standards, Bureau of Standards, BIS, which gives approval for a lot of things. So through that, we'll be able to find if anything is registered.
Well, what I understood from your presentation, that, well, finally, it's more or less similar to what we have in Europe, that you have some devices that work, supportive devices for registered medical practitioners, and then responsibility is with the doctor. And probably for these devices, you don't need to have some extra registration, because finally doctor decides about its use and he or she takes the full responsibility.
Full responsibility.
Yeah.
Yeah.
But what about the autonomous? You mentioned about the automated AI devices. In this case, do you have any special certificate for autonomous or automated AI devices?
Autonomous or whatever is the equipment which has been taken from FDA approval, taken from United States. Those equipments with FDA, we are trying to do it here, but there is a manual component to it, because Indian government does not accept the diagnosis of the equipment. The full responsibility is with the doctor who is using it. So every autonomous thing, doctor is checking. Manual thing is there. It is not without that, because telemedicine guidelines does not allow.
I see. Thank you. Well,
Andre, I just want to add a couple of things. So the list that I was talking about in my talk, it's publicly available. Anyone can download the list, and it's actually quite detailed. So it talks about the field of the medical device, the name of the products, the company that makes the products, and through which pathway within the FDA it was approved. So it really is quite comprehensive. And there's also a new initiative at the FDA now, where if you are a medical AI company trying to go through the approval process, they will actually help you get the insurance payers to the table, to the negotiation early on. Because what we've seen in the US is that there's several other big companies with a value, one of them is called Pear Therapeutics, with an initial market capitalization rate of 4 billion US dollars. They still went bankrupt because they couldn't figure out the reimbursement piece ahead of time. So there's a movement now within US FDA to really play matchmaking between the medical AI device companies and the insurance payers early on, so that the incentives are aligned from day one.
Thank you for this comment. Yeah. Any other questions from each of you to other speakers? If you do you have any questions? Well, I will just inform that we prepare such a session at every meeting, because every meeting I'm the president of this society will be held in November in Valencia, and we prepare a collaborative session with the National Eye Institute on the, let's say, US Europe collaboration in AI, on the let's say limitations for AI applications, and so for those of you who would be interested, please join us for this session and this meeting. There are few American speakers coming for this session, and we also provide from European part also European speakers. Okay, thank you so much for being.
Where in Malaysia? You said Malaysia. Where in Malaysia?
Valencia, and Spain. In Spain, every meeting is
Spain.
Spain, European.
Valencia.
Valencia is a you can find it information ever. European Association for Eye and Vision Research. This is European AVO. Easily find on internet. If you put ever and I, then you can get the society website and the Congress website, different websites, and of course more than happy to have of course you or other people from the audience to this session. Okay, so if there are no more...
One more thing. How about ChatGPT? Which is the large language model, ChatGPT, which is coming up.
Yeah, we had a whole session on ChatGPT, as a matter of fact, today. You know, the whole session with the first session was mostly devoted to ChatGPT. There were 2 talks on that, and the whole discussion with Professor Siama Kusefi on that. So possibly you can follow that. I mean, I don't think we should repeat the same topics again that were already presented and discussed during the meeting. Yeah, but of course, very promising topic, I would say. Promising. Yeah. Okay, if there are no other issues regarding the regulatory or legal issues related to AI, then I would like to thank you again, and also end the meeting this year. I would like to remind that everybody is welcome to register to our society. Now we have over 1,400 members, so I'm very happy about that. We have a few sections that started working. We will send you in the newsletter of the society the information in July, some minutes from these meetings. These meetings are still being held, so everybody is welcome to join each section within the society. So thank you so much. Thank you, everybody, and stay in touch within our society.